Hey, what's up everybody? Welcome back to the channel. In this video, I'm going to be going over all of the organic chemistry that you need to know for the MCAT. If you don't know who I am, my name is Naman. I'm a third-year med student. A couple of years ago, I took the MCAT. I got 100 percentile, and these review sheets made by a Redditor named Miles Down was one of the main ways that I used to review all the content that I needed to know for the MCAT. So yeah, without further ado, let's go into it. So what is organic chemistry? The first thing is IUPAC naming conventions. And to be honest, in the entire organic chemistry, all these 12 pages, this was the hardest page for me to understand. And actually, after a lot of trials of reading through this and trying to understand all the naming rules, what I actually ended up doing is I went through all the websites I could find. And this website was actually the most helpful in understanding the IUPAC naming rules. And so instead of, you can read all these steps and kind of just get a brief overview of what this is, but how I actually learned it was to look at some examples and understand what is actually the way that you name compounds. And I'll go through some high yield ways to look at different compounds and why they're structured the way they are, and then we can go over the rules after that. So the first thing to know is that we have these alkanes, and alkanes are just saturated hydrocarbons. The most important thing to know about organic chemistry is that it's all about carbons and hydrogens, right? And we actually, alkanes is kind of the basis of this. This is when a carbon is paired with all hydrogens around it and other carbons. So a CH4 methane, that's just CH C bonded to 4 hydrogens around it. And another way we can represent this is just a dot. And in organic chemistry, we can use a lot of dots and lines to represent compounds. So you can use methane like this. You can do ethane like that. You can do something like heptane by like 1, 2, 3, 4, 5, 6, 7. So that's heptane, right? That's the compound. So that's how we represent different compounds, and that's for alkanes. So let's look at some examples. Over here, the most important different brand substituents you should know is isopropyl and sec-butyl. And I'll show you how to name these and how to draw them with the examples we look below. So here, I'm going to go over this example, 4-ethyl 2-methylhexane. So here we first start with our hexane, which is 6 carbons, and we have to look at the longest chain here. So we have 1, 2, 3, 4, 5, 6. That's 6 carbons. Another way we can look at this is 1, 2, 3, 4, 5, 6. So basically, this chain or this chain are the longest carbons, and they're both equal, so that we just choose one. So I'm going to choose this one. So that's hexane, and then we need to know that there's on the second carbon, there's a methyl group, and on the 1, 2, 3, 4, on the 4th carbon, there's an ethyl group. So that's basically how we're naming 4-ethyl 2-methylhexane. Okay, the next one we'll look at is this one, because I think this is a good example. So here we have, starting with nonane, so we know that the longest chain has 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, and we can see that this is the longest chain. It's not this, it's not like that, right? It's this one. So it's nonane. That's our kind of the parent chain. Then we look at what are all the substituents. So I see one substituent here, one substituent here, and then one substituent here, right? So this is the second carbon. So, and then this is the 7th carbon. So I see 2,7-dimethyl. That's this part. Okay, this is 2,7-dimethyl. We have a nonane here, and then we have a 5, and then we need to figure out what this thing is. And I'm just going to draw this out because it'll be easier to understand. So this is basically the substituent is, I see a carbon over here, so carbon over here, and then we have another carbon this way, and another carbon this way, and this, right? That's the same thing as this. This and this are the same thing. So what is this substituent? So if you looked above, and you remembered what I told you, for the MCAT, the two most important ones you remember are these two. So this is sec-butyl, and honestly, it's not too important that you know these, but those are kind of the two most important. I would also know tert-butyl and isobutyl. And you should know sec-butyl looks like this, and isopropyl looks like this. So if you remember what I was drawing, it was like that. That is sec-butyl. So on the 5 carbon, we have a sec-butyl. Okay, 5-sec-butyl, 2,7-dimethyl, nonane. So now those are saturated hydrocarbons. Now let's look at, this is a very simple addition, which is, sorry about that, which is we're adding halides. And if you remember on the periodic table, halogens are just those those atoms in the 7th column, right? And those are fluoride, chloride, bromide, iodide, And the way we represent that is just a prefix with fluoro, chloro, bromo, iodo. It's pretty simple. It should make sense. The main example I want to look at here is this one. And the reason why I'm looking at this example is because it'll help you figure out how do you choose these numbers. So here we can choose the parent chain going in two ways. It can either go this way or it can go this way, right? So how do I know whether this chain is 1, 2, 3, 4, or is it 1, 2, 3, 4? The way that I choose that is I just look at the substituents, and bromo comes before methyl, and so we give this precedence. And so it's 2 bromo, 3 methyl butane, so the chain goes this way. Okay, next we're going to look at alkenes and alkynes. So alkenes are double bonded carbons, and alkynes are triple bonded carbons. So far we've looked at saturated carbons, which means they have all their bonds to hydrogen or to a halogen or something like that. But here we're looking at atoms that have now double bonds between them or triple bonds. So the examples that I'm going to look at here is 3-pentene, 1-ine. How do we figure this out? Well, the parent chain has a pent in it, so I know it has 5 carbons. So 1, 2, 3, 4, 5. That makes sense. And then we have a 3. This 3 is referring to this ene. Remember, ene is a double bond. So we know that on the 3rd carbon there's a double bond. And then this 1 is referring to ine. So that's on the 1 carbon there's a triple bond. So this is 1, 2, 3, 4, 5. On the 1 carbon there's a triple bond. On the 3rd carbon, 1, 2, 3. On this 3rd carbon there's a double bond. So that should make sense. All right, let's keep going. Alcohols. Alcohols are very, very important for your MCAT. They're going to have probably a compound with an alcohol in it, just because when we go into further in organic chemistry, we'll talk about like Sn1, Sn2 reactions, and alcohols show up in a lot of MCAT questions regarding substitution or elimination reactions. So let's look at this. The main thing to know about naming alcohols is you add an "-ol" to the end of the compound name. So 2,3-butan-diol. By now you shouldn't have to look at this, and you should be able to draw what that looks like. But basically we know that there's four carbons, 1, 2, 3, 4. Then on the 2 and 3 we have alcohols. And remember, the di means 2 alcohols, so there's on the 2nd and 3rd carbon there's an alcohol. Okay, let's talk about this one too. I haven't talked about cyclo, but cyclo basically means that you have a ring of carbons. So this is a we would add the prefix cyclo to it. Cyclopent means that there's 5 carbons in a ring, right? That's cyclopent. And then we know that there's a 1-ol. So in the first carbon there's a alcohol, and then in the 2nd carbon over here there's a ene, which means a double bond. So far this should be making sense. Now we have ethers. Ethers and esters, those are always really confusing to me. But it's important to know ether is when you have an oxygen that's part of that chain, and like it's bonded to 2 carbons, right? So that's what an ether is. And ethers are actually some of the easiest to name, because all you have to really do is look at what's on each side of the ether, of the oxygen, and that just gives you the name. So here you end with ether, and then what's on each side? One is a methyl and the other one is ethyl. So this is just ethyl, methyl, ether. What's on each side of these of this oxygen here? There's one ethyl and there's another ethyl, so it's diethyl ether. All right, we're almost done with the really high yield things to name. I think it's mainly this aldehyde and then this ketone that's kind of really important to get through. So the aldehydes is when you have a C double bonded to an O, and then you have an H at the end, right? This is important to differentiate from a carboxylic acid, which is like a C double bonded to an O to an OH, right? So aldehydes are without this O over here. It's C double bonded to O attached to an H. So what is the suffix we give? It's an al, right? Remember, for alcohol it was all. For aldehyde it's an al. So propanol is just 3 carbons, and we don't have to say 1 propanol, because it's obvious that the aldehyde has to be at the end of that chain, right? The aldehyde can't be in the middle of the chain. It can only be at the end, because the carbon isn't attached to a hydrogen. All right. The next one we'll look at is, let's do a little bit of a harder one, benzaldehyde. So if you're just following with this video, you wouldn't know what a benzaldehyde, like the benzo ring, is, but Hopefully in your organic chemistry class you've encountered, or 100% in your organic chemistry class you would have encountered like a benzo ring, and this is just referring, this structure, which you might have seen before, is just referring to like a ring where you have like these double bonds. And so you have 3 double bonds in this 6 carbon ring, and that's kind of what this is referring to. So benzaldehyde is this ring that's attached to an aldehyde over here. Okay, last one we'll go over is the ketone, and ketones are also kind of easy to name. They're kind of, it's kind of easy to remember because you just have this own suffix. So remember, we had the -al suffix for alcohols, we had the -al suffix for aldehydes, now we have the -one suffix for ketone, right? And here this one is the one I'm going to name here. So 2,4-pentane dione. So pent, 5 carbons, 1, 2, 3, 4, 5. Then we have 2 and 4 dione. So at the 2 and the 4 carbons, we have 2 ketones. All right. So fortunately, we've actually gone through pretty much everything on this page. So I'm just going to run through this, and hopefully with those examples we'll be able to cover all these things. So first step is find the parent chain, the longest carbon chain, and then that longest carbon chain has to contain the highest priority functional group. So there's actually like in the IUPAC naming conventions you can figure out what has the highest priority and which one has the lowest priority. Fortunately for us, it's not going to be always too big of an issue for the MCAT. I don't think I've encountered too many questions that have asked me which priority group, which functional group has higher priority, but it might be helpful to kind of just look at the priority of functional groups. Okay, then you number the chain in such a way that the highest priority functional group receives the lowest possible number. So remember when we were looking at a chain of 4 carbons and one of them was attached to a halogen, one of them is attached to a methyl, and then we were trying to figure out which one is the 2 carbon and which one is the 3 carbon. This is how you figure out which way you look at it, which is that you look at which functional group has the higher priority. In that case, the halogen had the higher priority. Next, you name the substituents with a prefix. So multiples, like you saw when I had compounds with 2 alcohols, we use the prefix or the suffix diol. Same thing when we had 2 methyl groups attached in a carbon chain, we use the prefix di for dimethyl. So that's kind of what this rule is saying. Next, we have step 4, which is assign a number to each substituent dependent on the carbon to which it's bound. So that's when we said like 4,7 dimethyl and then pentane, right? That's what this rule is saying. And then finally, we alphabetize the substituents. So if you were wondering why like ethyl came before methyl, well, it's just the alphabet. That's the only reason why we had like ethyl, methyl, ether. Versus like, why would you not name it methyl ethyl ether? Technically it's the same thing, but by IUPAC naming conventions we go alphabetically for naming those substituents. Okay, next we have hydrocarbons and alcohols. So again, we already talked about this. This is kind of a helpful formula to figure out, well, if every carbon is saturated with all the hydrogens attached, then how many hydrogens are there? So in this compound, there's 1, 2, 3, 4, 5, 6 carbons. So then based on that, you should be able to say, like, you should be able to tell me quickly how many hydrogens would be in this compound, right? And how you would figure that out is N is 6, so the number of hydrogens would be 14. Okay. Next we have alkanes are named based on the ane, so that's when we get pentane for 5 carbons. Alkenes use the suffix -ene, alkynes use the suffix -ine, alcohols use the suffix -ol, and then diol. This is kind of not that important, or I guess not that high yield, the germinal versus vicinal. Germinal means that the hydroxyl groups are on the same carbon. So if I had a 3 carbon parent ring and we had the 2 oxygens on the same carbon, right? 2 alcohols on the same carbon, that would be a geminal. Versus vicinal is when they're on adjacent carbons. So this is the same chain, but the 2 alcohols are on adjacent carbons. That's what that's saying. Okay. Again, I've never actually seen a question that was asking me the difference between a geminal and vicinal, so not too important. Okay, next is aldehyde and ketone, which again we just went through, and then we have, let's go through primary, secondary, and tertiary. So this is important. Amines amines is when you have nitrogens, and then alcohol is when you have these OH groups, right? Primary means that there's the OH group is attached to the carbon on the end, and that carbon is just bonded to other hydrogens other than its adjacent carbon and other than the alcohol group. So this would be a hydrogen, and this would be the rest of the ring, right? So this is a primary carbon. Versus, let's say now that your carbon is bonded to two other carbons, a hydrogen and your alcohol group. Well, in this case, we would say your alcohol group is on a secondary carbon, right? So that's a secondary alcohol. Now, a tertiary alcohol is when that carbon is not bonded to any other hydrogens. It's only bonded to other carbons and your alcohol. That is called a tertiary alcohol. So how I remember this is a tertiary alcohol, your carbon is attached to 3 other carbons. A secondary alcohol, your carbon is attached to 2 other carbons. And your primary alcohol, your carbon's attached to 1 other carbon. Amines are kind of very similar. Amines is when you have the nitrogen in the middle, and a tertiary amine is when your nitrogen is bonded to 3 carbons. These are all carbons. And then your secondary is when it's bonded to 2 carbons. And then your primary amine is when it's bonded to 1 carbon. Okay, so when you're looking at this, you might be asking me, well, how do I, these should be CH3, all right, you get the point. So you might be asking me, well, what about this 4th thing? What is that bonded to? And remember, nitrogen on the periodic table, it's in that 5th column, right? So you can just have the 2 electrons on the nitrogen, and then it's bonded to 3 other things, and this nitrogen is happy. So that's why you have this lone pair over here. Okay, let's keep going. So I walked you through all of them. I would know the names for 1 through 10. After that, I don't really care about all this. Carboxylic acids, we went over that. Remember, the naming for this is oic acid. Your carbon is double bonded to an oxygen, just like it is an aldehyde, but it's also bonded to this like OH group. And here, we don't call this OH group an alcohol. We actually call it part of the carboxylic acid. So that's an important distinction. Then we have esters. Esters is when you have, it's kind of like this carboxylic acid, but I was always confused, like, what does this R mean? Is that just the same thing as this H? And actually what you would see in an ester is like C double bonded to O, single bonded to O, and then you would have like the rest of the chain, whatever it is, right? And then here you would have the rest of the chain, whatever that is, and that's an ester. Okay, an amide is kind of like when you take a carboxylic acid, but you, instead of this alcohol over here, instead of this OH group, you have the nitrogen, and then that's bonded to other things. So amide, I kind of think of it as like when you have a carboxylic acid that is combining with an amine, right over here. And I'm going to go through this in biochemistry, but that's kind of a really helpful way to think about what is an amide, because these amides are really important and they're found in some important biological structure. And that's just kind of a hint for what's going to come in the future, which is just a question. Maybe you can answer it in the comments, but what is the biological structure in which you find amides very commonly in your body? Okay. So amide, again, they replace your OH group of the carboxylic acid with an amino group that may or may not be substituted. Okay, let's keep going. Okay, the next thing is structural isomers, and I'll be honest, in my organic chemistry class, I always had a lot of trouble figuring out what are all the different isomers and trying to organize it into my head, like what is an enantiomer and things like that. And so the best way that I learned this was looking at a lot of Google images and trying to understand, like, what do the compounds actually look like? So that's how I'm going to teach this page. So the first thing is structural isomers. Structural isomers share only the molecular formula, but they have both different physical and chemical properties. What does that mean? Well, basically, it just has the molecular formula be the same. So it's like C6H12O6. I'm sure you've seen that compound before. But there's a lot of different ways we can represent this, right? You can have like the carbons all attached to each other and then oxygens attached to the carbons, right? Or you could have like a carbon or you can have like a ring somehow, and there's oxygens attached to it. Maybe the oxygen is attached to the same carbon, or one oxygen is attached to each different carbon, right? So that's kind of how you can understand structural isomers. They only share the molecular formula, but the chemical properties, the physical orientation, the ways that the atoms are bonded to each other, they can all be different, and so that's what structural isomers are. Next, we have stereoisomers, and these are like way more similar than structural isomers. Stereoisomers is when you have compounds with atoms that are connected in the same order but differing in 3D orientation. So in that example I was giving you C6H12O6, I told you that in a structural isomer you can have two compounds that look completely different, right? Like the carbons can each be attached to an oxygen, or one carbon can be attached to all 6 oxygens somehow, and then the others are not attached to it, right? That wouldn't really make sense, but you get the idea that in a structural isomer, the two structural isomers can be different, like the atoms can be connected to each other differently. But in a stereoisomer, the compounds with atoms are connected in the same order. So those like C6H12O6, those atoms have to be attached to each other in the same order. So if I say like each carbon is attached to each oxygen, then two stereoisomers, that has to be true for both of them. The only difference is in what like shape and angle are those atoms bonded to each other. And the important thing to know here is that we have things called chiral centers, and chiral centers is when you have 4 different groups that are attached to a central carbon. If you don't have a chiral center, then it is not technically a stereoisomer. The simplest example I can give you is methane. So methane is when you have C bonded to 4 H's, right? So no matter how I change the direction of these bonds, like I try to flip them, I try to like move them around, there's no way that I can get a different methane molecule, right? Because no matter how you bond those hydrogens together, and then you tell me like, oh, this methane is different from this methane, since it's just one carbon that's bonded to 4 different hydrogens, it's always going to be the same. But in something like let's show you. Okay, I have a good example here. So in something like this compound, where you have a carbon that's attached to 4 different groups, right? You have a hydrogen, you have an oxygen, you have another carbon, you have a carboxylic acid, right? So there's 4 different groups here, and so this and this are stereoisomers, and to be more precise, they're going to be configurational enantiomers, which I'll go into later. But basically they're stereoisomers because they are, these atoms around this chiral center are oriented differently. Basically this dotted line means that the OH is going behind that carbon, behind our page, and this bolded line means that this is coming out of the page, right? So here this is coming out of the page in both instances. But no matter how much I try to move this around, like I try to move this over here, there's no way that I can move this molecule in such a way, like I can't rotate this molecule in such a way that these are still bonded in the same configuration. The only way that I can make this look like this is if I break the bond and then reattach the bond at a different spot. And you can kind of like try to play with this yourself, but the best way that I eventually convinced myself that this was true is I used one of those kits in our class, and I just kind of like tried to force myself to make 2 different enantiomers look like each other, or 2 different stereoisomers look like each other, and I couldn't do it unless I took out a piece and then put it back in at a different location. So that's how you know that you have a stereoisomer. Now stereoisomers again need chiral centers, which means that there's 4 different groups attached to the central carbon. If you have something like a methane, for example, you're not going to have 4 different groups, and so that is not a chiral center. Now we have conformational isomers. So I'm going to go over like how you can organize all these isomers over here, and it's going to make them a lot more sense, but for now I just want to give you examples so it makes sense. So we have conformational isomers. So it's not really too important that you know like what anti is, gauche, and eclipsed, like unless you're right now studying for organic chemistry, your final exam or something. But for the MCAT, it's not too important to know what's the difference between these. What's more important is you understand the concept. So anti, I'll just go over it because it helps me understand. But anti is when you have like this carbon, right? In the highest I guess, weighted group is this CH3 over here. And the highest weighted group in the carbon behind this is this CH3 group here. And what this whole circle thing is representing is this carbon is in front, and it's bonded to a carbon behind this that has this H, and this CH3 that's attached to that in the back. So this carbon in front is bonded to this, and this, and the carbon in the back is bonded to this, and this. Okay, anti is when you have those two bulky substituent groups on the opposite side of each other. And if you had to guess, would this be more or less stable than something like this? And hopefully you're thinking, okay, this is probably going to be a little bit more stable because these bulky groups are away from each other. The closer they are to each other, the more they kind of like repel each other, / they don't like to occupy that same space. So something like gauche is going to be more unstable than something like anti. Okay, so that's kind of how you think about conformational isomers. Conformational isomers is just like when you're kind of just rotating those things, right? Versus, yeah, so that's what a conformational isomer is. You're just rotating it across these, you're just rotating the two carbons so that like a gauche conformation is when you have these two bulky groups closer together, versus like an eclipsed is like in this orientation where they're not exactly anti, but they're a little bit closer than that. So that's kind of how you can think about conformational isomers. Okay, now we have configurational isomers. So next we're talking about structural isomers. Structural isomers share only the molecular formula, but they have different physical and chemical properties. So I think that the best way to learn about isomers is actually to look at a ton of examples, which is what I'm going to do with you when I'm going through this, because in my organic chemistry class, when I was trying to understand this, our professor was just reading the definitions but never showed us any examples, and it was really confusing to me. So I think looking at examples would be the best way to look at this. So this is an example of structural isomers. They have the same formula because they have the same carbons, right? The same number of carbons. They have the same number of oxygens over here and over here, and they have the same number of hydrogens that are attached to the carbons. But the atoms are connected differently. So the atoms here, the oxygens are attached to each other, the oxygens are apart from each other here. And with structural isomers, you can kind of get creative and imagine every single way that you can combine these different atoms together, as long as the formula is the same, like whatever this is, C4O2 something, whatever. As long as that formula is the same, the molecular formula, it's going to be a structural isomer, no matter how you combine those atoms. So that's what a structural isomer is. Now let's look at stereoisomers. So stereoisomers are actually just about as similar as you're going to get for compounds. Stereoisomers is when you have a compound with atoms that are connected in the same order but different 3D orientations. So stereoisomers are like when you have a compound that's like, it's really, really similar to this other compound, but like if you rotated this compound a little bit, like you rotated the atoms somewhat around the chiral center, then you would have a stereoisomer. So a good way to think about this is to first talk about what is a chiral center. Chiral centers are basically when you have a central carbon that's attached to 4 different groups. An example is right here, and we're going to talk about these type of isomers later, but this is just an example of a chiral center. This carbon is attached to 4 different things: a hydrogen, the alcohol, the CH3, and then the carboxylic acid, right? So that's what a chiral center is. Something like methane, where you're attached to 4 hydrogens, you can imagine that that's not a chiral center. And the reason why that matters is because a chiral center, when you're rotating this chiral center, then those 4 different groups are now oriented differently in space as compared to a neighboring chiral center. So how can I describe this? Basically, let's look at this example. The anti means that the 2 bulky groups are on opposite sides. And first, let's talk about how to actually interpret these, because I was always confused about this. But basically, how you interpret this is this circle, this front circle, you have a carbon, and the carbon is in the front, and this front carbon is attached to a CH3, a hydrogen, and another hydrogen. Okay, Now, behind this carbon, there's another carbon, okay? And that carbon is attached to this CH3, it's attached to this hydrogen, and it's attached to this hydrogen. And you can imagine that now we can kind of orient these two carbons so that if you rotated the front carbon a little bit, then you can imagine that this CH3 is going to be either close to this other CH3 or it's going to be as far away as possible. This is when you have it as far away as possible. And when you have it as far away as possible, that's called anti-configuration. It's not too important that you remember like what is anti, what is gauche, what is eclipse. You might need to know that for your Orgo class, but for MCAT, it's not that important. But you should kind of be able to reason to yourself, is this more or less stable than gauche, where you have the CH3 groups closer together? Well, you should be thinking to yourself, this CH3 group is as far away from this CH3 group, so it's probably more stable because these bulky substituent groups probably don't like to be occupying the same space. And so that's why the anti-configuration is more stable. But that's what basically a conformational isomer is. Basically, if you can imagine like two different carbons, and those carbons have different substituents, right, off of them, and then you're rotating one carbon relative to the other, then that's a conformational isomer, because even though technically it's basically the same compound, one of them now you've rotated it, and so you have these different conformations. So that's what a stereoisomer is. That's what a conformational isomer is. Okay. Now, this conformational isomer, basically all that's happening is that you just differ by rotation around a single bond. Now, what are cyclohexane substituents? This is not that important, but equatorial is when you have it in the plane of the molecule, the substituents, and axial is when it's sticking up and down from the molecule's plane. Okay, now we have configurational isomers, and this is when you get to those words enantiomers and diastereomers, and I remember everybody used to be really scared about these words in our Orgo class because it was really hard to understand, and I remember us learning about like these mirror image things, and I never understood like what is a mirror image versus like what is left versus right-handed thing. So hopefully you're not getting like bad flashbacks from Orgo class like I am, but that's basically what configurational isomers is referring to. You have these things called enantiomers, and enantiomers are mirror image molecules from each other. So you can think that like this compound is basically the same thing as this, right? But they're actually isomers. And why are they isomers? Because if you made this compound and you took it from this tiny space and you like exploded it so that it was right in front of you, and then you tried to basically like rotate these bonds around this chiral center, around this carbon over here, and you try to rotate the bonds so that this would look like this, right? You would find that you actually couldn't rotate these bonds. Like, let's just keep this hydrogen up top, and then let's just try to imagine that these substituents are rotating this way, right? So if you tried to rotate it around, you would actually find that it would not look like this. These are actually different, and they're different because they're mirror images of each other, and this carbon is a chiral center. It has 4 different substituents around it. And when you have those combination of factors, that's called an enantiomer. They're non-superimposable mirror images, and they have opposite stereochemistry at every single chiral carbon. They have the same chemical and physical properties, except that their rotation or their plane polarized light is different. But for now, I just want you to understand, like, why is this a different compound than this? Well, because if you rotated it around, it would not look the same. So again, if you blew it up and you tried to reconfigure this to look like this, you would actually have to break the bond and reposition it at a different space to make this look like this. It wouldn't work if you just rotated that. All right, so that's what an enantiomer is. It's when you have a mirror image. So you can imagine if I put a mirror over here, then this reflection would be like this. That's what that's referring to. Okay, now we have optical activity. So you can imagine that if we put like light through this like one of them would like have the ability to polarize it right, and the other one would be able to polarize it left. This is honestly just kind of a way that we classify which enantiomer are we talking about. Are we talking about the plus enantiomer or the minus enantiomer? Are we talking about the left one or the right one? And so you can imagine like chemists when they're making a type of medicine and they're making like one type of enantiomer versus another, like they want to be able to classify it. And so being able to say like which way does it rotate the plane polarized light, that helps them classify what type of compound, which enantiomer are they talking about. Racemic mixtures are when you have 50-50 mixtures of two enantiomers, and you can understand why that would not be optically active, because those rotations cancel each other out. Okay, now we have mesocomp. All right, so this is an example of chiral center, of meso compounds. So here we can kind of see that even though this is a chiral center and this is a chiral center, right? This is bonded to carbon chain, an alcohol, and it's bonded to a hydrogen, right? Same with this. These are both chiral centers, but because there's this plane of symmetry in this compound, this is, if we flip this over and we made both these OH groups go behind the plane instead of in front of the plane, that compound is going to be the same as this compound. It's not going to be an isomer. Now, this compound is indeed different. This is an isomer of this, because here one of those is going behind and one of them is going in front. So it's not like both of them are going behind, right? So in this case, this and this are isomers, but if we had a compound that was like, this is a striped line and this is also a striped line, that would be the same compound as this, because all we'd be doing is just flipping this over. And so that's why it's important to notice, like, do we have any like line of symmetries in this compound that would describe it as meso compound? And hopefully that explanation makes sense. If it doesn't, then just look through more of these examples. It'll make more sense once you kind of are able to identify these planes of symmetry. Okay, the next thing, we just went through meso compounds, and we talked about enantiomers, right? Enantiomers are types of configurational isomers. Then you might be asking, okay, so I know that there's configurational isomers, but there must be more than just enantiomers. What are the other ones called? Those other ones are called diastereomers. These are any stereoisomers that are not mirror images. Okay, so this is an example of a diastereoisomer. So in this case, we have like this is going out of the page, this is going into the page, and this is going out of the page, right? And it's the same as this. So these two are the same. But then let's look at over here, right? So here we see that this is out of the page, this is out of the page, this is into the page. Same thing here, but these are flipped, right? And you can imagine that this bottom thing, if we tried to rotate it, we wouldn't be able to make it look like this. So these are isomers of each other. These are configurational isomers, but they're not enantiomers, because if I put a mirror here, this part kind of looks like a mirror, this part is not a mirror image of itself. So these two compounds are diastereomers of each other. They are configurational isomers that are not enantiomers. That's the definition of a diastereomer. Okay, then we have cis-trans. These are a different subtype of diastereomer. These are basically stereoisomers that are they're stereoisomers in which they have different chemical and different physical properties, and they differ at some but not all of the chiral centers. So I want to show you an example of that. So this is an example of cis-trans isomers, and this might actually show up on your MCAT. I remember on my exam it did. But you have this double bond over here, and then you have, remember, around a double bond you can't rotate it the same way you could around a single bond. So you have these chlorides that are upward, and here the chlorides are going away from each other. This is called trans because the chlorides are on opposite sides. This is called cis because the chlorides are on the same side. So that's cis-trans diastereomer. These two compounds are not the same. They're isomers of each other because the chlorides are on different spots in this and in this, and because you can't rotate it around a double bond or a triple bond. Okay, now we talked about everything on this side. Let's go over relative and absolute configuration. Relative configuration is basically the stereochemistry of a compound in comparison to another compound. D and L, to be honest, these are kind of lower yield than absolute configuration. Absolute configuration is kind of more important for the purposes of organic chemistry, and this is when you define something as S or R. And that's when I'm telling you, like, if I was going to tell you this compound is oriented in the S configuration, and I told you what the substituents were, you'd be able to kind of draw it out and like tell me how are these oriented in space. So that's our convention for describing that. So this is basically the priority rules. This is how you define things. And priority is given by looking at atoms connected to the chiral carbon or double bonded carbons. Whichever one has the highest atomic number gets the highest priority. So if we're looking at a chloride and a fluoride, then the chloride would get priority because it's a higher atomic number. Now we have Z and E. This is kind of similar to the cis-trans things I was telling you. So Z means the higher priority is on the same side. E means the higher priority is on the opposite sides. Now R and S is for stereocenters, and this is, remember what I was telling you is important for organic chemistry. It will probably show up on your exam as well. R, we look, we say like the lowest, we basically, I think it would be helpful to go through an example of this, but basically what you're going to be doing is you're going to look at a stereocenter and you're going to configure it so that the lowest priority group is in the back. So you like reorient the compound so that the lowest priority group is in the back, and then you draw a circle from the priority 1, priority 2, and priority 3. And if this circle goes clockwise like this, then we say that's R configuration. If it goes counterclockwise like this, then it goes in the S configuration. I'll go through an example. Now we have Fisher projections. Fisher projections, it's not super important that you know how to draw something in Fisher projection, but I would just know that vertical lines go back of the page and horizontal lines come out of the page. So that's basically, this is what this is referring to. Those are Fisher projections. Now, altering Fisher projections, it's not too important that you know how to do this, but you can read over this. Okay, this is kind of a very, very helpful diagram that helped me a lot in like organizing myself. So I never tried to memorize all this, but I did just kind of go through it and make sure that it made sense. So the first thing that we're looking at is it the same molecular formula? If it's not, then that is not even, we're not even considering that because those are just two different compounds. We're talking about isomers here. So if they have the same molecular formula, then it's an isomer. That means that it's like the same atoms, right? But now we have to ask, are those atoms connected to each other in the same way? So if I'm saying like CO2 is, you know, is it like CO2 where one carbon is double bonded to two oxygens, or is it like one carbon bonded with three bonds to one oxygen, one bond to the other oxygen, and like some electron? Like basically, are the connectivity the same, right? So if it's not, then it's a constitutional isomer. If it is, then we keep going, and that's called a stereoisomer. Now, stereoisomers, remember when I said like we blow it up and we have to rotate it? If we can rotate it and it doesn't break any bonds, then those are really, really similar compounds, because basically all you're doing is you're just rotating it, and the only difference is the fact that it's just oriented differently in space. And so that's called a conformer or a conformational isomer. But if we do have to break bonds, that's when, remember, we were talking about enantiomers and diastereomers. Those are what we're going into here. So if we do have to break bonds to rotate it in the way that it needs to be rotated, like it's impossible to rotate it, you have to break a bond and reconfigure it, that's called a configurational isomer. Now, configurational isomers, if it's a mirror image of each other, then it's an enantiomer. If it's not, then it's diastereomer. So this is a really helpful flow chart to get through this whole thing. Okay, I promised you that I would explain how you would do an R and S naming. So in this example, you have to look at this and you figure out that the lowest priority is this H, right? Now you can see, okay, so we have the H, we forced it to go in the back, and now we number these. So bromide is going to be the highest, then it's going to be chloride, then it's going to be fluoride. So we start with 1, and then it's 2, and then it's 3. So this is counterclockwise, so it's an S. On the other hand, here it's clockwise, so it's an R. And that's kind of how you can think about R and S configuration. Now the tough thing for me was always like pushing the lowest order thing in the back. And so that thing is going to take a little bit more effort on your part in terms of visualizing it. when the lowest priority group is not in the back. So that's what we're looking at here. So here it's like this H is going forward and we need to push it back in order for this to work. So in your head, you kind of have to 3D rotate this thing so that we force this H to go in the back, right? So if you 3D rotate this and you imagine like pushing it back, then you have to imagine like, okay, when we're pushing this back, like imagine that it's coming towards you. Now this H, we're going to push it back, and because we're pushing it back, this amine that's in the back now comes forward, right? So now it's pointing downward and forward, and then you can imagine that like if this is in the plane, now it's going to push forward, and if this is in the plane, it's also going to push forward. So that's basically you can imagine like rotating it like this, and if you do that, then this is going to turn into this. Once you do that, now we can number these. So the N is the highest number, then the C is the second number, then the methyl is the third number, right? The reason why this C is a higher number than this methyl is because this methyl is then bonded to hydrogens, whereas this C is then bonded to oxygens. So now we go this way. Is that clockwise or is that counterclockwise? To me, that looks like counterclockwise, so that would be an S configuration. Okay, so that's how you figure that out. Okay, the next thing that we have to talk about is bonding, and this is actually a very high yield chapter, even though it's pretty short, but I remember this giving me a lot of trouble when I was in my organic chemistry class, so I'm going to do my best to explain it in a way that makes sense, in a way that I understand it, not necessarily how I was taught and the formal way of understanding it. So this stuff should be familiar from the Gen Chem video that I made. So if it's not, just check that out. It'll make more sense. But basically, quantum numbers is how we describe atomic orbitals in an element. And an atomic orbital is eventually, over hundreds of years, if you watch the general chemistry video, you'll see like the progression of how we understood an atom, and eventually we came up to this probabilistic model in which we figured out, okay, there's this nucleus in the center of the atom, and then around it we have electrons. And where do those electrons occupy space? Well, we don't really know, but we do have a pretty good idea by taking snapshots of an atom. And by taking snapshots of an atom, like imagine you're holding a camera and you take a picture of the atom, you can find like, oh, this electron is right here, these electrons are right here for that 1 second, and then you take another snapshot and you figure out like, oh, these electrons are right here, and then you take another snapshot and it's like right there, and you combine like millions and millions of these snapshots, and eventually you figure out, okay, 95% of my snapshots, the electron was within this space, and that space is called an orbital. And so we have different types of orbitals, like an s orbital looks like this, a p orbital looks like this, and then there's d orbitals and f orbitals, and that's kind of what the shape of an orbital is, right? That's what this thing is, the 3D shape. So 0 is s, 1 is p, 2 is d orbital. So that's what that's referring to. The principal quantum number is like, what shell are we occupying? So that's kind of how far is that electron from the nucleus, and by telling us how far it is, it also tells us what energy level is that electron. So you can imagine that if the electron exists pretty far away from this nucleus is positive charge and this electron is negative charge. So that's a different energy level than if this electron was right next to the nucleus. Okay, then we have magnetic and spin numbers, and in Orgo class these were never explained that clearly. It's always kind of like a hand-wavy explanation of what these mean. But basically magnetic, you can kind of think of it as a way to figure out how many orbitals exist in that type of shape. So if I was going to take a p orbital, that's the 1, p equals 1, then I want to know how many p orbitals are there. And if you count this, then it'll be -1, 0, and 1. And the way that magnetic number is kind of a way to designate which p orbital are we talking about. Are we talking about the -1, the 0, or the 1? And then there's the spin. Basically, you should know that there's 2 electrons within that orbital subtype, in each orbital subtype, and so we give one of those numbers kind of arbitrarily a positive and the other one a negative. So that's what those numbers mean. Now these are helpful formulas, but you should be able to reason through these formulas and figure out, based on what I explained to you, why is this true? And if you can do that, then you'll be good to go. So the maximum electrons in N, so let's just use N as 1. So in the first electron energy level, there's 2 maximum electrons. In the second energy level, there is 2 times 4, so there's 8, right? And we should be able to figure out why is there 8 in the second energy level. Well, if we do all this math, then we'll figure out, okay, so there's the L is 0, 1, right? That's the L possibilities. And for each L, there's this one just has 1 orbital, and then this one, remember we talked about -1, 0, 1. So that's 1, 2, 3, 4 total orbitals in the second energy level. And there's 4 total orbitals, and we know each orbital has 2 electrons, so times 2 is 8. So that's how we get to that number. That's what this is referring to. If that doesn't make sense, just do the math for yourself. Try to figure out why in the second energy orbital are there 8 maximum electrons. Finally, we have the subshell, and you should be able to derive that using this formula. And I'll leave that to you, and hopefully you'll be able to do it. All right, the next thing is molecular orbitals. So far we've kind of been dealing with this in a little bit of a simple way. We've been talking about a single atom, but we know that atoms don't just exist alone. They want to bond with each other, like CO2 or NO2 or any of the compounds. You know that atoms like to bind to each other. And so now chemists in our history of chemistry are thinking, well, how do I justify that these atoms are bonding to each other when I have this like orbital theory of, you know, these electrons occupy some space 95% of the time. And how they explain it is they explain molecular orbitals. This is different from atomic orbitals. Atomic orbitals are describing one atom, like carbon or gold. Molecular orbitals are talking about compounds, so carbon dioxide or water. Those require molecular orbitals. So molecular orbitals are basically saying, the theory behind this is that we take 2 atoms and we say that these atoms, yes, they have their own atomic orbitals, but when they come together, they form a molecular orbital. So they're kind of combining, they're overlapping space of their individual atomic orbitals, and by overlapping those spaces, they form this new thing called a molecular orbital. So that's kind of how I finally came to understand it, and that's the best way that it made sense to me. So that's what a bonding orbital is. Now, anti-bonding orbital, you can imagine that if you have, we've kind of given all these atomic orbitals different numbers, right? Positive, negative, and all those things. So now we can imagine that if we take 2 orbitals, 2 atomic orbitals, and we put them together, they can either be high energy or low energy. Basically, when they're low energy, when they're more stable, that's a bonding orbital. And when we take 2 atomic orbitals and they're not exactly like, they don't exactly want to gel together as easily as bonding orbitals, those are called anti-bonding orbitals. So that's kind of a simple way to think about it. Now, when we're overlapping orbitals, we can imagine that, you know, some compounds, the atoms want to form double bonds or triple bonds, right? They don't just want to form a single bond. And when we do that, we have to actually say, okay, we're overlapping multiple orbitals there, and over there we're saying we're going to call them different types of bonds. Your first bond, your single bond, is a sigma bond, and then after that we form pi bonds. So a triple bond, this contains 1 sigma bond and then 2 pi bonds. That's kind of how we think about it. And multiple bonds, you should know, is less flexible than a single bond. And you remember when I was talking about rotation around a bond? Well, a single bond can rotate. So these, like if this was oxygen and this was an H and there's another H over here, right? This is not a good example, but let's talk about a different example where, let me find an example for you. So this is actually a good example. So H2O, if this is a single bond, so this can rotate around the single bond. But if you had a double bond in the compound, then it would not be able to rotate. All right, the final thing I'll mention about molecular orbitals and double and triple bonds is that you should know that like 2 bonds obviously is stronger than 1 bond, but the first bond, that sigma bond, is stronger than the second bond, pi bond. But together, these are stronger than just 1 sigma bond. That should make sense. Okay. All right, next is hybridization. So we should know that this is kind of a way to characterize different types of molecular orbitals. So you can imagine that if I'm taking, I'll show you examples of all these compounds so it'll make more sense, but basically these are ways to characterize what is the characteristics of the molecular orbital that you're looking at. And so if I was going to say I want to take like an S from the H atom, and then a P from the O atom, right? These are the orbitals that we're taking, and we're sharing electrons between these, right? You can imagine that there's going to be, we want to understand what is the characteristic of that new molecular orbital. We know what the characteristics of the S is, and we know what the characteristic of the P is, but what is this new characteristic? And I'll show you examples of how we can figure out which one of these it's going to look like. All right, so I'll go into examples, but I want to keep going with this. Resonance is basically the delocalization of electrons in a molecule that has conjugated bonds. So remember I was talking to you about this benzo, and we have this ring, and this is kind of equivalent to these double bonds, right? And so in organic chemistry, it's really important to understand that this is actually going to exist half the time, and this other molecule is going to exist the other half of the time, right? So because these electrons, you can just kind of, they like to kind of bounce around and be shared among all the 6 carbons. So what does that mean? That is basically what we'd refer to as resonance. It's kind of a characteristic of organic chemistry, is that electrons in conjugated bonds, they like to be delocalized if possible. Then this kind of goes into conjugation. Conjugation is when you have single and multiple bonds that alternate, creating a system of unhybridized p orbitals down the backbone of the molecule through which pi electrons can delocalize. So that's exactly what I was just saying. We refer to that as conjugation. Okay, I'm going to show you examples of this so that it makes more sense. So we'll start with the characteristics, and then we'll go into resonance and conjugation. All right, here's the example that I wanted to show you of the types of carbon-carbon sigma bonds. So this is various compounds in which we're looking at different types of sigma bonds that these carbons form. So over here, this is the simplest one. These are 2 sp3 orbitals that are next to each other. And this is kind of describing the molecular orbital that these electrons in this sigma bond occupy. And sp3 next to each other, this is basically just saying that this carbon has is bonded to 4 different things, right? Is bonded to 3 hydrogens and then another carbon. And so when that happens, we refer to that sigma bond as sp3. So this sigma bond between this carbon and this carbon is 2 sp3s that are together. So that should make sense. Next, we have a sp3 and an sp sigma bond. So this again is a carbon that's bonded to 4 different things, 3 hydrogens and 1 carbon. This one, however, is actually just bonded to 2 things, right? One is the other carbon, and the other one is another carbon. This carbon has 3 bonds too, so 1 sigma bond and then 2 pi bonds. So we refer to this carbon as an sp. It has an sp configuration, and this carbon has a sp3 configuration. So this is a sp3 sp sigma bond. That's basically describing the electrons that exist in this molecular orbital. Now let's talk about this. This is bonded to 2 things, so it's an sp, whereas this is bonded to 1, 2, 3 things, right? There's a double bond here, so this is sp2. All right, so you kind of get the idea of what these orbitals are describing. Now we should know, what are the characteristics? Well, a characteristic is pretty simple. The sp3 molecular orbital has 75% characteristics of a p orbital, 25% characteristic of an s orbital. You can do the breakdown for sp. Sp is 50-50, sp2 is like 33-66. So that's how you can think of that. Next we can talk about conjugation and resonance. So this is conjugated double bonds, right? And we can see that when electrons kind of like to float around in this resonance space, in this conjugated space, because they're lower energy that way. So you can imagine that this has a lot of conjugation, because these double bonds can actually hop around. Like this can go there, this can go there, and then this can go there, right? And so, or another way that we can think of this is both of these electrons in this pi bond can actually jump onto this carbon, and so this carbon is going to get 2 electrons, right? And it's going to get a negative charge. So that's another way where these electrons can all kind of hop around and exist in any space. And so if you're actually looking at a benzo ring, and again, you took like a camera and you tried to take snapshots of this benzo ring, you might see it existing in a variety of different in a variety of different configurations depending on the time that you're looking at it, right? It's not always going to look exactly like this. It might look some of the time like this, right? Or it might exist some of the time like this, negative charge over here, and then like double bond, right? And then maybe like a positive charge over here. So those electrons are happy to kind of just jump around, right? So that's what we refer to as resonance. And so because of that, this is going to be a very stable, low energy configuration. Now, this is a little bit more high energy, low stability than this, because there still is conjugation. You can kind of hop these double bonds around, but not as much as in this ring form here. So this is going to be still conjugated. And here we just have one double bond. And so because we don't have the system of like double bonds next to each other and alternating carbons, this double bond is not going to be able to hop around the same way that it was in this configuration. And so this is going to be isolated. It's not going to be having resonance with different compounds. And because of that, it's going to be the highest energy, lowest stability in this three. Okay. Okay, now that we've covered a lot of the basics of organic chemistry, now we're going to get into the really nitty-gritty, the reaction stuff, and the organic reaction specifically. So if you remember, a lot of this stuff is from Gen Chem, so make sure you watch the Gen Chem video before this. But first we need to identify what are these types of acids. So there's different types of people, Lewis, Bronsted, Lowry. These people defined acids and bases in different ways. The most important way that it's that you'll have to define it for organic chemistry is Lewis acids and Lewis bases. So you're probably used to the definition from Bronsted, Lowry, acids and bases, which is that you know, an acid is like something like H2SO4, where you donate these hydrogens, these protons. But this guy Lewis defined it as an electron acceptor, electron donor, and that's how we're going to define it in organic chemistry for the most part. So get used to that definition. Next, we have amphoteric molecules. These are things that can either be acids or bases. Things like H, CO3. This is mostly just a base, but maybe like H2, this is a better one, H2PO4 minus, right? That is a amphoteric molecule. It can either donate or accept electrons. It can either donate or accept protons. Those are amphoteric molecules. Then we have Ka and pKa. These are the same thing, just represented as a log of the other one. Ka is the acid dissociation constant. I talked about this in the Gen Chem video, but it's basically just a measure of acidity. So you can imagine that if we have a really strong acid, HCl, right, it doesn't really exist. We just kind of say is HCl, but really if you put it into water, it's just going to dissociate immediately into H plus and Cl minus. And so the Ka of this is really quite high. And the Ha of something that's a weaker acid is going to be closer to something like 0. And so this is the acid dissociation constant. pKa is just the negative log of this, and it's really important to know, and they might kind of test you on this, but it's important to know that pKa decreases down the periodic table and increases with electronegativity. And basically the important thing to know here is if your Ka is high, the log of that Ka is going to be high. The negative sign is going to make it lower. So you can imagine like something with a pKa of -1 versus like, you just have to understand like that like it's kind of the opposite of Ka in terms of going up and going down. Okay, now we have alpha carbons, alpha hydrogens. I've kind of already talked about this, but if you have like a carbonyl and then a carbon and a carbon, right? This carbon is called alpha carbon. This hydrogen is called the alpha hydrogen. It's the one that's right next to the carbonyl carbon. This carbon is not like this one is not the alpha carbon. This is the carbonyl carbon. Okay. Now let's talk about redox reactions, chemoselectivity, and we'll get to everybody's favorite topic, which is, you know, the types of reactions, Sn1, Sn2, and elimination reactions. So Redox reactions, I've again talked about this. This is kind of review. You have oxidation numbers, you have oxidation, reduction. I'm not going to go too much into this because I've already talked about this in Gen Chem. Then we have chemoselectivity. So chemoselectivity is basically the idea that both nucleophiles and electrophiles and redox reactions, they all tend to act at the highest priority functional group. So what is a nucleophile and what is an electrophile? Well, it's kind of in the name. If you know Latin roots, phile means liking it. So nucleophile likes nucleus, electrophiles like electrons. And then you can make use of steric hindrance properties. I remember this word all the time from organic chemistry, and it actually took me a couple of days to actually search this up and understand what it means. It just means like how bulky is your group, right? If it's like some really bulky group that takes up a lot of space and it's heavy, then other things might not want to be in the same space as it. It might make a good leaving group, but that's just one property of it that you have to look at. Okay, so it's just kind of important to keep some rules in mind. You can use steric hindrance properties, you can use functional groups, and then you can pay attention to what type of solution your reaction is happening in, and it'll help you guide what type of reaction is going to happen. Is it Sn1 as Sn2, elimination, E1 or E2? So now let's talk about your favorite topic, which is these type of reactions. What are these? And so what I want to mention here is that there's basically going to be a nucleophile in these reactions. There's going to be there's not going to be like another compound that's reacting with this in these elimination reactions, but what's happening is that these reactions are taking place in a basic solution. Okay, so now that we have that out of the way, we need to know two things about these reactions. One is that there's going to be something that's attacking this in a substitution reaction. This nucleophile is going to be attacking this molecule. Okay, and then the next thing to know is that in all of these we have to pay attention to what is this reaction, what solution is it taking place in? Is it taking place in water? Is it taking place in acetic acid? Is it taking place in acetone? All of these have solvents that they're taking place in. So they're not happening in the air, they're happening in a solution, in a beaker. You have some liquid, you put in these compounds, and then you see what happens to it. So those are the two things to pay attention. Now we need to know what's happening in each of them. Substitution reactions, Sn1 and Sn2, describe the fact that this nucleophile is basically replacing your leaving group. So in this case, there's a chloride that leaves and the nucleophile replaces that. That's called a substitution reaction, right? Substitution, replacing. Same thing happens in Sn2 reactions. Now we need to know the difference between these two. And basically, the difference is going to be in how many steps does it take for this to happen. In Sn1 reactions, it takes 2 steps to have that. First, this guy, I'm going to wait. Okay, first the chloride leaves this, and then the nucleophile attacks. In this one, the nucleophile attacks this, and the chloride leaves in the same step. So that's the difference between Sn1 and Sn2. Now we have elimination, E1 and E2. In both of those, we're going to get rid of this, and it's called the leaving group. So in both of these, the leaving group is going to leave. And same thing, it depends on whether it happens in 1 step or 2 steps, and that's kind of how you determine if it's E1 or E2. All right. So now let's talk about all these rules. So nucleophiles, as I mentioned, is nucleus loving. They contain lone pairs or pi bonds. They're high electronegativity. They carry a negative charge. And amino groups are the most common organic nucleophiles. Why is this? Well, if you can think of an amino group, right, NH3 bonded to something. This is an amino group. Well, why is this a nucleus loving compound? Because it has those 2 lone pairs, it has electrons and wants to be added to something. All right, nucleophilicity is just a kinetic property. It means the nucleophile's strength, right? You can imagine that how strong is a nucleophile? Well, it depends on its charge, it depends on its electronegativity, it depends on the steric hindrance, it depends on the solvent. And so how strong is your nucleophile? That's going to depend on your that's going to describe your nucleophilicity. Now we have electrophiles. Electrophiles are electron loving, and they contain a positive charge or they're positively polarized. And there are more positive compounds. So the compound that's more positively charged is going to be more electrophilic. Why is this? Because if it has a positive charge, what does it want? It wants a negative charge. What are electrons? Negatively charged. So that's why more positively charged things are going to be more electrophilic. They're going to want electrons more. All right. Now we have leaving groups. Leaving groups are these things that I told you about here, this chloride over here, this chloride over here. Those are all leaving groups. Those are the things that leave, and they're the molecular fragments. The best leaving group is able to stabilize the additional charge that it's leaving with. So why is chloride leaving this? Well, because the nucleophile is attacking this compound over here, and what's happening is that this chloride is leaving with the electrons from this bond. This bond, the electrons go on to this chloride. So what is this chloride going to look like when it's leaving? It's going to look like that. It's going to be a chloride ion, right? But chloride is a halogen, so it's very happy to take this extra electron, and it makes a good leaving group. And that's why the nucleophile is going to attack right here, because it knows that this chloride is a good leaving group, and so it's going to stabilize that additional negative charge, either through resonance or induction, or it's just going to be like a halogen. It's going to be something that is able to stabilize that additional negative charge that it's leaving with. All right, now let's talk about Sn1 and Sn2. And I've hinted about this already, but Sn1 reactions happen in 2 steps. In the first step, the leaving group leaves and it forms a carbocation. In the second step, the nucleophile attacks that carbocation from either side, and it's going to result in a racemic mixture of products. So do you remember when I was talking about enantiomers? You can have 2 different types of enantiomers based on the mirror image of each other. In an Sn1 reaction, you're going to have this compound. It's going to be, half of them is going to be R, half of them is going to be S. All right, so based on what I've told you now, you shouldn't be able to think about, well, if this is leaving the first step, right, then the carbocation is going to be right here. There's going to be a positive charge right on this carbon. Well, this proton, this like positively charged particle, it's actually more stable in this place where there's multiple different carbons that are attached to it. So these carbons are kind of able to handle this positive charge carbon, versus over here, if this chloride were to leave and this positive charge were over here, this carbocation is not that stable, because it's not really going to like having hydrogens next to it and having having only one carbon next to it, right? You can imagine, like, let's say you're a carbon, right, and you're attached to all hydrogens. Okay, these are all hydrogens. And now I'm telling you, okay, I'm going to take away one of the hydrogens, and you're going to be stuck with a positive charge, right? Somehow I'm going to get rid of this guy. This is gone. And now this carbon is a positive charged thing, right? Well, these hydrogens are not going to take away, this carbon is going to have the majority of the electrons now, because it's taking like the majority of the electrons in each of those bonds with the hydrogen. And then it also has a positive charge. So it's not going to be like stabilized that well, versus a carbon that's attached to other carbons, right? These carbons are going to be able to handle like a positive charge better than if it was attached to hydrogens. So basically, Sn1 reactions are more likely to happen when you have like secondary or tertiary carbons, versus Sn2 reactions are more likely to happen when you have like a primary carbon. And the reason for that is because in Sn2 reaction, all of this is happening in the same step. So you're not stuck with a carbocation for too long. It's just all going to happen in one step. Versus here, you're kind of stuck with this carbocation for a while. And so because of that, this needs to be stabilized by other carbons that are attached to it. All right, so I hope that makes sense why you'll have Sn1 reaction and why you'll have an Sn2 reaction in different types of molecules. The next thing to know is the rate of this depends on the rate limiting step. Remember, there's 2 steps here, and so only the rate limiting step is going to determine the rate here. What is the rate limiting step? It's going to be dependent on that substrate. So how much substrate you have times rate constant is going to be the rate of your reaction. Next, you'll have Sn2 reactions. Sn2 reactions all happens in one step, and the nucleophile attacks at the same time the leaving group leaves, and the nucleophile is doing a backside attack. So basically what that means is initially if the particle with that leaving group is an S configuration, now the nucleophile attacks, and this is going to change the configuration into an S configuration. So there's an inversion of stereochemistry. MCAT likes to ask you about that. Now, Sn2 prefers less substituted carbons because steric hindrance inhibits nucleophile from accessing the electrophilic substrate carbon. That should make sense based on what I explained to you before. But here, the rate is actually dependent on both the nucleophile and the substrate. So I feel like MCAT likes to test this indirectly, which is if they ask you, like, there's this much substrate and this much nucleophile, and it's a Sn1 reaction, and this is the rate constant, and people will multiply all of those things, the nucleophile. But the nucleophile, the amount of nucleophile doesn't actually affect the rate of an Sn1 reaction, but it does in an Sn2 reaction, because everything is happening in one step. Okay. All right, I hope that makes sense. Now let's talk about the polar protic and polar aprotic solvents. So this is all just kind of stuff you have to memorize. Fortunately, it's not that bad. You should know that water is polar and protic. I guess I should talk about protic means like it has hydrogens, so there's like hydrogen bonding, and that's going to be able to stabilize some of these like positive charges or negative charges, and so that's just something to know. All right, so now that you know that, it's not too hard to know which ones are polar and protic, right? Like these ones have H's in them. You should be able to understand why they're going to have like hydrogen bonding, and then they're also like all polar, so it should make sense. Versus polar aprotic, these are all kind of like the longer names, and it should make sense why these are polar aprotic. So it shouldn't be too hard to memorize this, but that's like kind of important that you understand which ones are polar and which ones are non-polar, and which ones are protic and which ones are not aprotic. And all of these in this are all polar. All right, now we have to talk about this chart, and this chart is the highest yield thing on this page. It's very important that you understand this chart. You don't have to memorize it, but you do have to understand it. So I think that these two columns, everything right here should make sense so far based on what we've talked about. What we said is that these methyl, right, these like methyl carbons / these primary carbons, they're not going to enjoy just having a positive charge. It's going to be too unstable. And so because of that, they're not going to like the Sn1 reactions where you have a carbocation for an extended period of time. And so because of that, you're not going to see Sn1 in any of this. You're actually not going to see it in this whole row. So it's only going to be Sn2 reactions here. Same thing, you're not going to see any Sn1 reactions here in a primary. This thing is not going to like being a carbocation. But in a secondary and a tertiary, you're going to see some elimination reactions. And the reason, you're going to see some Sn1 reactions. You're also going to see some elimination reactions, which I'll talk about. But this is okay with being a carbocation because it's able to stabilize that. And so that's why you're going to see more Sn1s, less Sn2s, okay? All right, so that should kind of make sense so far on these. Now we should talk about we'll go row by row. So here we know that we're going to have all Sn2 reactions. So this is all going to happen in one step. This guy is going to leave. It's going to be a leaving group, and this guy is going to be added by a it's going to be replaced by a nucleophile. All of these are Sn2 reactions. It doesn't matter if you're in a polar aprotic, polar protic solvent. It doesn't matter if it's a strong base, strong small base. It doesn't matter if it's a strong bulky base, right? Now we have primary, and it's almost the same thing, but in a strong bulky base, let's say you have like a really big nucleophile, right? Like this nucleophile that's replacing this bromine. So this is a really bulky base that's replacing this guy over here. Well, this carbon might not actually want to be attached to a really bulky base in replacement of this replacement of this bromide. So what's going to happen is, in the case of a really strong and bulky base, what's going to happen is that this guy is just going to leave, and then this is just going to have a double bond over here, and these electrons will just go onto the bromine. This will become a leaving group, and then there'll be a double bond here. That's an E2 reaction. So I would know that for a methyl, you're going to have all Sn2s. For a primary carbon, you're going to have all Sn2s unless it's a strong bulky base, in which case it's probably going to favor an elimination reaction. Why is it E2 over E1? Well, it should make sense why, because this guy doesn't want to be a carbocation for too long. Okay, next we have secondary. Secondary is a little more difficult because you're going to kind of see a bigger spectrum of things, right? You see like Sn1, E1, Sn2, E2. So, well, let's talk about this versus this. First, let's talk about polar aprotic versus polar protic. In a polar protic solvent, this guy is positively charged, right? What's going to happen is this thing is going to be positively charged, and it's going to be actually stabilized a little bit better with all these hydrogens attached to, let's say water is in the solvent, right? You're going to have these negatively charged oxygens, that are like electronegative, and these are going to be able to stabilize that positive cation over here. So this oxygen that's bonded to two hydrogens and the lone pair over here, that is going to stabilize this carbocation, and so that's why it's more willing to accept these two steps rather than all having it in one step. In an aprotic, those that like hydrogen bonded to like an oxygen, that oxygen won't be able to stabilize this, and so it's less likely to become a carbocation, more likely to just all happen in one step. So that's why you can have Sn1. Here you can either do Sn1 or E1. Just what will probably happen is if this reaction happens in a polar protic solvent, you will see some Sn1 results and you will see some E1 results. You won't see like complete Sn1 products. So that's that. That explains these two. Now, why are these elimination? Well, whether or not you have a strong small base or a strong bulky base, you're not going to have Sn2 here because there's too many carbons attached to this, and so it's not going to be a Sn2 reaction. It's kind of hard for the substitution to happen and for this backside attack to happen. So you're going to get an elimination reaction. Why is it E2 rather than E1? Well, you know that E1 is happening over here. E2 is going to happen when there's that strong small base or strong bulky base. There's basically this basic solution. It's going to let's look at the elimination reaction. So this is the elimination reaction, right? There's that double bond. So basically what's going to happen here is that you're going to have this strong bulky base or strong small base just help replace this with a double bond. So that should make sense. Then finally, you have tertiary. In tertiary, you'll probably see some more E1s in your polar protic solvents or your polar aprotic solvents. If you have a strong small base or strong bulky base, again, you're just going to have E2 results here. And so that should kind of make sense to you that it's elimination rather than substitution reactions as a result, because there's just too many carbons that are attached to this guy. The base is not going to want to attack this and replace the bromide. Instead, what's going to happen is that there's just going to be elimination and there's going to be a double bond somewhere based on where the base is helping this leaving group eliminate from. So that's a very important chart. Honestly, it's more important to know these two columns. Those are going to probably show up on the MCAT. This is going to show up a little bit less, and what I've seen in most of the practice questions that I did in the past and like most of the questions that show up on all the exams is they like to ask about substitution a lot more than they like to ask about elimination. I would more know like if they're giving you like this is the solution, this is the solvent, this is a methyl carbon, they're going to ask you like, oh, is this a, like they might ask you something like, oh, is the result going to be an R or an S, and or is it going to be like a mixture of them? And that's going to help you like figure out, well, is this a Sn1 reaction or Sn2 reaction? You should know the methyl carbon wants the Sn2 more. All right, so that's a very high yield concept. Try to go through that again. Just make sure you understand this chart right here. Okay, let's just keep going through this. So we have alcohols and phenols. Alcohols have that ROH, so there's this carbon chain and it's bonded to OH group. This is alcohol. It's probably going to be the most common substituent that shows up in any of the Orgo questions. If they're usually highest priority. If they're not the highest priority, then you give the prefix hydroxy. If it's the highest priority, then you give the suffix -ol. Then we have phenols. Phenols are basically these benzo rings that have OH groups attached to it. And then you can describe the OH group instead of saying like 1,4, 1, 2, 3, 4. Yeah, 1,4 diol for this ring. You can say like the alcohols are in the para configuration versus the meta configuration versus ortho configuration. It's not going to show up very much on your MCAT. So next, we know that alcohols, they can hydrogen bond, so that hydrogen bonding causes increased boiling and melting temperature. That was in the Gen Chem section. Phenols are more acidic than other alcohols because the aromatic ring can delocalize the charge of the conjugate base. I've explained this, so this electron can jump around, and so these are very stable compounds. Why does that make the phenol more acidic? So why, if I have like this benzo ring attached to an OH group, why is this very acidic? Well, this H plus is going to leave. This O is going to have the negative charge from the bond between the O and the H. And now we have a O that has a negative charge, is that negative charge going to be well stabilized? Yes or no? It's going to be actually very well stabilized, because this negative charge is existing within a benzo ring in which the electrons are already like kind of hopping around, moving around everything, right? So what's going to happen is like this negative charge on the oxygen might go into that, and now we'll see like a double bond, like an what is this, a ketone, right? And these you might see like something like this, right? So the electrons are happy to jump around, and so that oxygen that has that negative charge is going to be very, very well stabilized. If that oxygen is well stabilized when the hydrogen is leaving the alcohol, is that phenol that we originally had, is that acidic, more acidic, or less acidic? It's going to be more acidic. Why? Because it's actually very happy for the hydrogen to leave. It's very happy to donate that hydrogen because this phenol is stabilizing that negative charge very well. Okay. Now we know that electron donating groups like alkyl groups decrease acidity because they destabilize negative charges. Electron withdrawing groups like electronegative atoms like F and oxygen, these and aromatic rings increase acidity because they stabilize the negative charges. So you can imagine, like, if I have this carbon chain and then I want to remove a hydrogen from this, and so this is now a negatively charged carbon. This does not like that because carbon is not that electronegative, right? And so it's not gonna like this extra electrons that much. But if you have like an oxygen, like an OH group, right? And you're saying like, I'm gonna get rid of this hydrogen and give you some more electrons. This oxygen is going to be probably a little bit better about having those electrons because it is electronegative. It's electron withdrawing, like it likes having electrons. So that's why like a alcohol is more acidic than like a alkyl group, because this is more electronegative. This is an electron withdrawing group, so that should make sense. Okay. Okay, now let's talk about reaction of phenols. So we should know what quinones are. They're not that important, but here we'll talk about quinones, which are synthesized through the oxidation of phenols. And basically, you remember that a phenol is like, it has that OH group off a benzo ring. So when we oxidize this, it actually becomes a ketone, and that's when you get quinones. Not that important here. Vitamin K and vitamin K1 and vitamin K2 are examples of biologically relevant quinones. I've never seen this show up on the MCAT, the vitamin K1 and K2. Okay, hydroxyquinones are basically produced by oxidation of quinones, and we add a variable number of hydroxyl groups. Then you have ubiquinone. This is kind of important for biochemistry. Ubiquinone is coenzyme A. That's one of the things in the electron transport chain. So when you're producing ATP from a molecule of glucose, you use this ubiquinone, which is coenzyme Q. All right. Next, let's talk about reaction of alcohols. This is kind of high yield as well. So reaction of alcohols, you'll notice that we have primary alcohol, secondary alcohol. Primary alcohol can be oxidized to aldehyde, and it's oxidized to aldehyde only by PCC. So when I say alcohol, I mean this thing, and if this is off some carbon chain, we want to oxidize it, let's say, to like an ketone, right? So, or we want to oxidize it to an aldehyde, right? How do we oxidize an OH group to an aldehyde? Well, we do it through PCC. And you might remember this from Orgo class. And one helpful kind of way of thinking about organic chemistry is all about manipulating different chemical reactions so that you take one molecule and you change it into the other molecule. And so if you can think of that like that, then we always want to understand, well, how can I take like an alcohol and make it into an aldehyde? The answer is PCC. And this is a primary alcohol. So remember, primary alcohols are just attached to that one of the carbons. It's not like in the middle of the chain. It's at the end of the chain. That's a primary alcohol. Now, secondary alcohols, you should know, are able to be oxidized to ketones, not aldehydes, and they're able to be oxidized to ketones by any common oxidizing agent. Okay, primary alcohols only by PCC. secondary alcohols by any common oxidizing agent. Then you should know alcohols can be converted to mesylates or tosylates to make them better leaving groups for nucleophilic substitution reactions. So mesylate is this thing, tosylate is this thing. To be honest, this was more important for my organic chemistry class than it ever was for the MCAT, but essentially you're taking this thing, which is an alcohol, which is a pretty good leaving group, but you can make it a better leaving group by converting it to this thing or converting it to this thing. And like a mesylate is basically the sulfur is the main atom and it's double bonded to two oxygens. The tosylate has this benzo ring that's attached to this sulfur, and that's why there's this silate thing. So that's kind of how I think about it. Mesylate is kind of like a methyl, right? Like the methyl is C and then 4 H's. Tosylate, I just remember there's a benzo ring there. Again, not too important for MCAT, more important for your Orgo class. Now we have aldehydes and ketones. So we just talked about alcohols being converted. Now we want to talk about aldehydes and ketones being protected from conversion. So they can be protected by converting them into acetals or ketals. So basically, let's say that I'm trying to do like I have this alcohol and I have like something, I have like this ketone in the middle of the chain, right? And let's say I'm trying to manipulate this reaction and change it into something else. So when I do something and I want to like oxidize this alcohol or do different things to this molecule, I might accidentally end up manipulating this ketone in the middle. And so I want to actually protect it if I want to keep the ketone as is. And that's what we're talking about here. So how do we protect these? Well, we protect them by converting them into acetals or ketals. Acetals look like this and ketals look like this. And for the MCAT organic chemistry and for your Orgo class, this is super, super high yield. This is like very, very important that you know what an acetal looks like, what a ketal looks like, and why converting aldehydes and ketones into these is important. For MCAT, it's also important, but I would try to just remember what an acetal looks like and what a ketal looks like. So ketals are pretty simple. You know that there's a ketone, right? Well, how do we change this into a ketal? Basically, we just do 2 OR groups instead of that one double bond to an oxygen. Acetal, well, it's the same thing, those 2 OR groups, but instead of this being in the middle of the chain, like it would be in a ketal, this is happening at the end of the chain. So we have 2 OR groups like that. So that's what an acetal is. So that's how we protect, and we convert it back into the aldehyde or ketone at the end of this. Okay, now we have deprotection, and this is how we convert the acetal or ketal back into the carbonyl, and we use a catalytic acid. So that's the reactions of alcohols. Now we have aldehydes and ketones. So aldehydes are terminal functional groups. I've already gone through this. You can use the suffix -al, which is normally how you use it, or if you're in a ring, you use the suffix carbaldehyde. Now we have ketones. Ketones are internally functional groups containing a carbonyl bonded to 2 alkyl groups, and you use -one or use oxy or use ketone. Now we have carbonyl. Carbonyl is a carbon-oxygen double bond, and I've already gone through this, but it's like when you have that. And the reactivity of a carbonyl is dictated by the polarity of the double bond. So the carbon has, like, it's partially positive. Why is that? Because the carbon is less electronegative than the oxygen that it's double bonded to, right? This oxygen wants these electrons in this double bond more than the carbon does. So this carbon is partially positive. This oxygen is partially negative. All right, that's basically what that's saying. Now we say have a higher blood pressure, have a higher boiling point than equivalent alkanes due to dipole interaction. So you should understand why this is true. If you're thinking about this, right, you have this partially negative and you have this partially positive. And then let's say you take a lot of these compounds and you put it together. Well, this oxygen is going to interact favorably with other carbons that are partially positive. And so you're going to have this little interaction that is kind of increasing the boiling point of that solution or that compound versus an alkane. Alkanes don't have that. The C and H, there's not really that much of like electro negativity difference between those, and so you're not going to have an increase in boiling point as compared to the carbonyl compounds. Now, alcohols have also higher boiling points, and it's important to know that alcohols have higher boiling points than carbonyls. And so in my organic chemistry class, I remember getting tested on this, and they asked me, why is it that alcohols have higher boiling points than carbonyls? The reason for that is hydrogen bonding is really strong, right? This hydrogen is partially positive, and there's going to be like other oxygens that are, sorry, this should be partially positive, oxygens that are partially negative, and these are going to hydrogen bond, and basically it's going to elevate the boiling point. So that's important to know. Now we know oxidation, I've already talked about this, but aldehydes and ketones are commonly produced by oxidation of primary and secondary alcohols. And if we want to synthesize an aldehyde, then we need to use a weaker oxidizing agent like PCC. And I mentioned PCC before, but why do we want to use a weaker oxidizing agent for producing an aldehyde? Well, the reason for that is because let's say I have this chain and I have a primary alcohol at the end of it, right? I want to oxidize this, and let's say I use a really strong oxidizing agent. What is going to end up at that end? What's actually going to end up is it's going to be this chain, and then it's going to be a double bond to oxygen, and then this OH. So this is a carboxylic acid. So if we take an primary alcohol and we oxidize it with too strong of an agent, it's going to result in that. So we don't want a really strong agent. What we want is we want this primary alcohol to end up into an aldehyde. And the way we do that, double bond to O and then H, that's an aldehyde. The way we do that is using a weak oxidizing agent called PCC. Okay, so hopefully that makes sense. Now we have oxidation and reduction reactions. Aldehydes can be oxidized to carboxylic acids, and they can be used pretty much any of the oxidizing agents because these are all pretty strong. So you can use this or this or this or this, and they can be reduced to primary alcohols via hydride reagents like this or this. So I would just kind of, I memorized this when I was taking the MCAT. So just know those are the oxidizing agents and reduction agents that would help convert the aldehyde into a carboxylic acid or into a primary alcohol. Now ketones can be further oxidized. Ketones cannot be further oxidized, right? This is the maximum oxidation that you're going to get to, but they can be reduced. What would they get reduced to? Well, an alcohol. And how do you reduce them? Well, you use the same hydride reagent. So you use like this lithium, or you use the sodium. So yeah. All right, so I would, for the MCAT, I memorized all of these. There's honestly not a lot to memorize, and these should all make sense. So PCC is a weak oxidizing agent, so if you have a primary alcohol, you can convert it to an aldehyde. If you have a secondary alcohol, then you can convert it to a ketone. These are stronger oxidizing agents, so if you have a primary alcohol, you'll result in a carboxylic acid. If you have a secondary alcohol, you'll get into a ketone. I've mentioned all of this, so this should all make sense to you. Now let's talk about the reducing agents. Reducing agents are pretty simple. Aldehydes and ketones, they're going to end up in primary and secondary alcohols. And then this one, it's going to result in primary and secondary alcohols in the same way. So what's the difference between these two? Well, for lithium, you can actually use it on like esters, right? You can use it on carboxylic acids, and you'll get primary and secondary alcohols. Versus, I wouldn't use sodium for those carboxylic acids and those esters to reduce them. So I would use this lithium, aluminum, hydrogen, LAH, it's called, to convert those into primary and secondary alcohols. But this one won't do the same thing. All right, so we've gone through a lot of high yield things right there. Let's keep going. Nucleophilic addition reactions. So nucleophilic addition reactions is when a nucleophile is attacking and forming a bond with those carbonyl carbons. This is going to happen a lot. I would say that in the MCAT, the most commonly tested reaction is not the substitution or elimination reactions, it's these nucleophilic addition reactions where a nucleophile is attacking that carbonyl carbon, and it's going to result in this reaction right here. So what's gonna happen is that nucleophile is forming a bond with the carbonyl carbon, and the electrons in the pi bond, so the pi bond is this bond right here, it is going to be pushed onto the oxygen atom. So what's going to happen is now it's going to be a single bond, and these electrons are going to go into the oxygen. If there's no good leaving group, then the carbonyl is just going to remain open, and it's going to be protonated to form an alcohol. So what that's saying is that when you have this carbonyl and it's getting formed to this, the electrons are going to this oxygen, then there's just going to be an H added to that oxygen, and it's going to be an alcohol. But if there's a good leaving group, carbonyl will reform and kick off the leaving group. So if this is happening to a carbonyl which is attached to like a chloride or something, right? Then if there's a substitution with a nucleophile, the nucleophile is going to attack here, the electron is going to go on to the oxygen, and then this chloride is going to leave, and this nucleophile is going to replace. So hopefully that makes sense. Now we have hydration reactions. Hydration reactions is when water is added to carbonyl. It forms a geminal diol. So remember, the geminal diol is where the two alcohols are on that same carbon. So this should make sense to you. This oxygen over here is attacking this carbon over here. So then you get this is basically forming an OH group here. The electrons from here go here. And because this is happening in this solution, the H will there'll be a donation of a proton here, and so you'll get one alcohol sticking off here and then one alcohol sticking off here. If that doesn't make sense, just watch a video or something, it'll make more sense, but just try to understand that reasoning that I just walked you through, because this is a very important reaction, and that's kind of this hydration reaction is an example of the nucleophile addition reaction. Okay, next is aldehydes and alcohols. So an aldehyde, I'm just going to walk you through this, and then I'll talk about this. But basically what's happening is that you have this aldehyde, and it's getting converted into a hemiacetal, and then if you do that again, then it'll be converted to acetyl group. So remember, the acetyl group is where you have these two ORs, and then you have an H off here, and then this is the rest of your carbon chain like it is over here, right? But what's happening in the middle is you're forming a hemiacetal. So what's happening is that instead of this being an OR group, it's just an OH. And so how do I explain that? Basically what's happening is this exact same thing that I explained to you up here with the nucleophile addition reactions, right? You just have to think through it a little bit. So what's happening is you have this, right, this nucleophile, it attacks right here to the carbonyl carbon. Remember, the carbonyl carbon is a really good place to attack because it's partially positive, right? These electrons want to go onto the oxygen more than they want to go into this carbon. So this thing attacks over here. And what you get is you result with these electrons wanting to go to this O. This O will pick up an H from the solution. So you get this OH. That's where this is coming from, right? From this guy. Then you have this OR. Where did that come from? That came from this attack. So this attack resulted in this bond being formed to an OR. Right? This ROH, it attacks, and OR gets bonded, and you result in a hemiacetal. Now, if you do that again, let's do that again. So this attacks, and then, well, do we have a good leaving group? Well, kind of, yeah, because if we donate a proton over here, or if we stabilize this with just the solution, right, this becomes a good leaving group, and then we result in two ORs. So that should make sense just based on the explanation I gave you before. Same thing with the ketone. The ketone, you have this attack over here. It results in an OR and an OH. If that happens again, this attack, then the OH becomes a leaving group, and then you have two ORs. That's a ketal. So that's exactly how that's happening. That should make sense to you. Review that if that doesn't make sense, because that's also very high yield. So what's happening here is the exact same process. So I think you should be able to walk yourself through why these reactions happen. So I would pause the video and try to walk through this yourself, and then I'll explain it. So basically what's happening is there's nitrogen and nitrogen derivatives, and they react with carbonyls to form imines, oximes, and hydrozones. The most important thing, and semicarbozones, but the most important one is imines. Imines is the one I would actually know. Imine is just this particle right here where you have the N double bonded to the C. So how is this happening? Basically there's this attack happening, right? It attacks this carbonyl carbon, this carbonyl carbon, this O has an OH, it becomes a reasonable leaving group. So this kind of leaves out, this N gets bonded to the C, this N is bonded to the R, the H2O comes from this oxygen. So that's how you get this. Now, the other important thing is, remember we talked about resonance? Well, there's resonance right here with the imine. Imines are able to be converted into enamines, and the way that happens is that this double bond over here, it can hop over here, and this lone pair can hop where that double bond was, and that's how you get an enamine. So this will exist in resonance. If you take a snapshot, some of the times it'll exist in this imine form, some of the times it'll exist in the enamine form. Okay, now we have hydrogen cyanide, and it reacts with carbonyls to form cyanohydrins. I wouldn't worry about that. Okay, now we're moving on to more aldehydes and ketones. Again, this is all really high yield. You'll get at least 1 or 2 reactions on your MCAT chemistry section in which you have these reactions going on. So we're going to go over more general principles right here. First thing to mention is there's this alpha carbon. Alpha carbon is the carbonyl. It's an alpha carbon. So you have this carbon, right? The carbon that it's next to is called an alpha carbon. The hydrogen that's attached to it is an alpha hydrogen. Okay, we've already talked about this, so I'm not going to go too much into it. And then you should know that those alpha hydrogens are relatively acidic. Why is that true? Well, this oxygen is actually liking to take electrons from everywhere around it, right? And so you can understand why these hydrogens would be more acidic. Try to explain that to yourself. It should make sense. And so because of that, these hydrogens, they're actually happy to leave. Because remember, acidic hydrogens, they want to leave the compound. So if you have an acidic hydrogen, these are happy to leave if you have a strong base. And what do you end up with? That's an enolate. And that enolate can be stabilized by resonance with the carbonyl. So I'm trying to show you how this would work. But let's say that a strong base picks this hydrogen up, it leaves, and then this these electrons in the single bond go on to this carbon, right? So now these electrons in this pi bond can go onto the oxygen. This picks up a negative charge. This carbon would pick up a positive charge, but actually this positive charge, because there's this guy has a negative charge, this is happy to form a double bond with the carbon. And so what you end up with is this structure right here. And so that structure can have resonance with this structure right here. And that's what happens when you have alpha hydrogens leaving. It's a stable structure that it's leaving behind. All right, hopefully that makes sense. It's basically the same thing as ketones, but what I will mention about ketones are they are less reactive towards nucleophiles than aldehydes because of the steric hindrance. So in an aldehyde, it's happening all at the end of the chain, right? Whereas a ketone, it's happening in the middle of the chain, so it's going to be a little bit less reactive towards nucleophiles. All right. Now we have enolate chemistry. So this is what I just mentioned. You have a keto form of acetone, you have enol form of acetone. The keto form is where there's a C double bonded to the oxygen, and the enol form is where you have the C single bonded to the oxygen but double bonded to the carbon. Now the question I'm going to ask you is this more stable or is this more stable? And hopefully you're thinking, well, this is going to be more stable because this carbon wants to have a double bond with oxygen more than it wants to have a double bond with carbon. That's why this is going to exist less in nature than this is going to exist. This is going to exist more in nature. And that's basically what this is saying right here. All right, now we have tautomers. Tautomers can be isomers that can be interconverted by moving a hydrogen and a double bond. So this is basically a tautomer because you're moving this electron and then you're moving a hydrogen from here to here. All right. And then you have Michael addition. Michael addition is when an enolate attacks an alpha beta unsaturated carbonyl generating a bond. And I'll show you some examples of this later. And then we have kinetic enolate versus thermodynamic enolate. No changes here. This is the same principle as before. Kinetic enolates will move faster at lower temperature, but they'll be less stable than a thermodynamic enolate. Finally, we have enamines. Enamines are tautomers of imine, like we talked about before. Okay, now we're on aldehyde. Aldol condensation. Aldol condensation is when you have an aldol addition to create an aldol that creates a new carbon-carbon bond. And then it undergoes dehydration to give a conjugated enone. So a conjugated enone is alpha-beta unsaturated carbonyl. All right, aldols, they have both aldehyde and an alcohol. And aldol, you just add the aldol. That's kind of like a way that some people think of it. It didn't really help me, but you're basically adding aldol, so aldehyde, alcohol. That's basically how that's what an aldol is. So aldol can be a nucleophile or electrophile. The nucleophile is the enolate formed by deprotonation of the alpha carbon. So remember, we're removing this, and that results in a nucleophile. And then you have an electrophile, and basically that electrophile is the aldehyde or ketone in the form of keto tautomer. So why is that true? Well, you can think of a keto tautomer, and you have that aldehyde, and this carbonyl right here is electrophilic because it wants electrons, and that's why the aldol is electrophilic and it's nucleophilic. Like there's different parts that are each of these. Now we have dehydration. You can have dehydration, which I'll show you over here, is basically when you lose the water molecule, and that happens because you're losing like an H and you're losing an OH from two separate places. So let's look at this. This is basically the dehydration part. So you're having this double bond form over here. How is that happening? Well, what's happening is that this guy is losing a hydrogen over here, and then this guy is losing an OH, right? And which OH is it losing? It's losing this one. So because you're losing an OH and you're losing a hydrogen, what you lose is water. So this guy, there's a water that's leaving this, and in place of that, because you've lost something from here and you've lost something from here, instead it's just forming a double bond. That's the dehydration reaction. Now let's look at the aldol reaction like we were talking about up here. What's happening over here? And again, this is very high yield for MCAT Orgo. All right, so what's happening over here is that this aldol reaction is essentially happening in this with this base component available. And so what's going to happen is that this base, remember I told you about how aldols can act as both nucleophiles and electrophiles, and the nucleophile is the enolate formed by deprotonation of the alpha carbon, and then the electrophile is in the form of the ketotautomer. So basically what's happening, and I'm going to show you a Google image that'll explain this really well, but basically what's happening is that this base is going to deprotonate this carbon over here. And so what we're going to get is like this with the double bond to the oxygen attached to the CH, and then this is only going to have two hydrogens attached to it, and it's going to have a lone pair on it. So there's going to be a negative charge on this carbon over here, And you might ask, well, why is it going to be like that? Why is that a stable configuration? And the reason why that's a reasonably stable configuration is because that has resonance with this other form of the same compound, which is this one. And so this would have resonance with this compound if we deprotonated this carbon over here. So that should make sense why that is a stable compound. And then when you think about it, when this base is deprotonating this carbon and the negative charge is on this, you can imagine that this is going to be very nucleophilic and this is going to be very electrophilic, right? And I told you why this particle can exist in nature, why this hydrogen actually is more desiring to leave, because it forms a pretty stable compound which has resonance. And so that's why this hydrogen is actually willing to leave, where you normally don't see like ethane, you don't see the hydrogen wanting to leave, but in this configuration the hydrogen is willing to leave because when it's leaving there's a stable configuration, or a reasonably stable configuration, with that negative charge being distributed across this oxygen, carbon, and carbon. Okay, so that should make sense so far. So now we've established that this is relatively nucleophilic and this carbon is relatively electrophilic. So it should make sense that there can be a attack on this compound. So imagine that I take two of these, right? So one is over here, and then I'm going to draw another one below it, so the exact same thing, but it's with that negative charge, right? And then the oxygen. Okay. So now you can imagine that this guy is going to come over and attack this guy, right? And what's going to happen is now you're going to have the same thing where you have that CH3, but now this, basically what you're going to get, and it's kind of hard to draw this out, but basically you have to kind of imagine this for a second with me. And what's going to happen is you can see that there's this original compound over here, right? But we've attacked it with this carbon over here. So basically what we're getting is you get this original compound where this is negative, this guy is the same as right here, right? And remember, this carbon is attacking this carbon on the next molecule. So you can imagine that this carbon is now attached to this carbon over here. And so that's why we get this. Because this carbon is being attacked, these electrons go on this oxygen. This oxygen picks up a proton from the environment, and so you get an OH group that's hanging off. That's equivalent to this guy. Then you have the two CH3 groups that are off the original compound. So those are the two CH3 groups over here and over here. So I remember that when I was studying this a couple of years ago, this part was pretty confusing to me. This dehydration part made a lot of sense to me. And I remember that in my Orgo class, I just decided that I was going to just memorize what is the product of an aldol reaction. But eventually when I got to MCAT studying and I kind of understood how do we take two of these compounds and then we form this compound over here, it made a lot more sense to me what this all was saying, aldol nucleophiles and aldol electrophiles. And so my explanation might not have made sense so far, but I'm going to show you a Google image and I'm going to walk you through it so it'll make more sense. So this is the best Google image that I could find that kind of explains this aldol reaction. Basically what's happening is we have this base, it deprotonates this carbon over here, right? The carbon that's attached to the aldehyde carbon over here. That's this carbon. So this carbon is going to be deprotonated. Because it's being deprotonated, we're going to have a lone pair of electrons, and this carbon is going to carry a negative charge. Remember, because this is carrying a negative charge, this shows resonance with this double bonded oxygen, because this double bond is happy to go over here. And then when we have this double bond over here, this oxygen picks up that negative charge that was on that carbon. So it should make sense based on our previous discussion why this is a more stable configuration, because it displays resonance, and so that lone pair is actually being distributed across that molecule. Okay, so now you should understand that, okay, we have this compound, and now we're going to do aldol addition, and then we'll do a dehydration reaction. So remember, we have an electrophile and we have a nucleophile, right? The nucleophile is going to attack the electrophile, and basically the nucleophile is this carbon over here, and it's attacking this carbon over here, which is more of an electrophile. So you can imagine this attack happening. This carbon is going to be bonded to this carbon, and basically this is very helpful because this is shown in blue and red, and so you can imagine that it's more helpful than that image I was showing you before, because now you can understand which compound is referring to which. And so you can imagine that if I draw a line between this and this, then these electrons go into the O, so it becomes O minus. So now you can understand that, okay, I have this part, this aldol, which is right here. Then I have this alpha carbon, which is right there, right? And that alpha carbon, remember, it has a methyl group off of it, so that's the same methyl group, but it's now also attached to this carbon over here. Okay, the carbon from this aldol group of the electrophile. So it's attached to that carbon of the electrophile. That hydrogen is still there, but we don't need to draw a line to it, right? We have this negative charge because those two electrons in that double bond have gone to the oxygen, so that's where this negative charge is coming from. And then remember, we have two carbons over there, so that's where these two carbons go from. So this should all make sense now. And then finally, we just remove a water. We do that dehydration reaction I was telling you about, and that's how we can get that configuration. So over here, they're showing like an addition of water, but you can kind of understand, or they're not really showing that dehydration component, but I'll show you that dehydration component again. So this was the dehydration component I was telling you about. So we remove that hydroxide from this carbon, and then we remove the hydrogen from this carbon, and then we can form that double bond over here. So that should make sense. Okay, so hopefully that all makes sense. If you understand this kind of aldol reaction and the dehydration that comes after, then you're pretty solid on understanding ketones and enols and aldol electrophiles and aldol nucleophiles. And believe it or not, this is actually a very high yield reaction for the MCAT. They love to test this because it kind of shows whether you understand what a nucleophile and electrophile are. Okay, now let's continue talking about carboxylic acids. Carboxylic acids, as I talked about before, they have that carbonyl group and a hydroxyl group, and it's attached to that carbon, and they're always terminal groups. So that basically what that means is that it's always at the end of the chain. You can't have a carboxylic acid that's in the middle of a chain. Nomenclature, you use the oic acids, and then if you have a salt, which means like you remove this hydrogen and you give this a negative charge, then it's a O8. Dicarboxylic acids are dioic acids. So if you have a chain where there's two carboxylic acids on the ends, and that's a dioic acid, that's the suffix. Then we have physical properties. You should understand that they're very polar. They hydrogen bond as well. They result in a high boiling point, and they often exist as dimers in solution. So why are they polar and hydrogen bond? Well, you can understand that this oxygen over here is pulling these electrons, right? And so that's why they're polar. You should understand that they can hydrogen bond. And so, yeah. Okay. Acidity. So the acidity of a carboxylic acid is enhanced by the resonance between its oxygen atoms. So what does that mean? This is also a very high yield point, mainly because if you understand it, then you'll get a better sense of what acidity means. But remember, acidity is kind of how willing is this hydrogen to leave, right? That's one of the ways that we define acidity. And, well, are we willing to get rid of this hydrogen? Let's see what it leaves behind. It would leave behind a negative charge on this oxygen. Is this negative charge stable or unstable? You should be thinking, well, it's actually pretty stable because there's this resonance thing where this could now form resonance when we get rid of this and we have that negative charge. This could form a resonance with this compound over here, which is basically the same thing, right? You can understand that this double bond will hop over here and this oxygen over here will pick up that negative charge. So because we have resonance, and because, remember, I told you resonance means that it's a more stable compound, because there's resonance with that base that is formed by this hydrogen leaving, that carboxylic acid is going to be pretty acidic. Okay. So the acidity can be further enhanced by substituents that are electron withdrawing and decreased by substituents that are electron donating. So why is it that the acidity can be further enhanced by substituents that are electron withdrawing? There's going to be an electron that's going to be on this oxygen, right? And if you can imagine that there's substituents that are electron withdrawing, then it's going to better be able to handle that negative charge. Okay, beta dicarboxylic acid's not that high yield, but it's just like other 1,3-dicarbonyl compounds. They have alpha hydrogens that are also highly acidic. So you can imagine that this hydrogen is highly acidic. Why is that? Well, this negative charge is going to be pretty well stabilized in this type of beta dicarboxylic acid. So, okay, let's keep going. So unfortunately, there's some reactions that you just have to memorize. These are some of them. This is basically describing a carboxylic acid synthesis. And remember, I told you organic chemistry is all about how you can synthesize compounds from different compounds. And so this is an example of when you take one compound and you use that KMNO4 that I told you about in the previous page. You do that under this reaction and you form this. Now, it is really important in your organic chemistry class that you kind of remember all these equations and how you can form one compound into a different compound, but for the purposes of MCAT, these types of equations are very low yield. So I'm going to tell you that it's important that you kind of look at it and understand, okay, I remember that KMNO4 is one of those oxidizing agents that can turn this compound into this compound and form a carboxylic acid. But beyond that, I'm not expecting you to remember that this is the specific compound that's in this reaction. This is another one where you just kind of have to memorize that, okay, we have a carboxylic acid. You use that LaH4, AlH4, which is one of those reducing, one of the things that reduces compounds. This reaction allows it to ultimately get reduced, right? So you can see that a carboxylic acid is getting reduced to an aldehyde, and then it's going to get reduced to an alkoxide ion, and then you just add a proton to that to get this into this. So essentially what you're taking is a carboxylic acid and you're reducing it in multiple steps into a primary alcohol. Okay, now we have nucleophilic acyl substitutions. This should make a lot of sense. It's nothing new that that we're going over right here, but basically you have this thing that's going to become a leaving group, and so what's going to happen is this nucleophile attacks this carbon on the carbonyl, right? And what's happening is this nucleophile is replacing this, and this becomes a leaving group. And so that's all that this whole thing is talking about. And why is this an appropriate compound for this nucleophile to attack? Remember, this carbon is kind of electrophilic, right? These electrons are more likely to hop onto this oxygen, and they're happy to hop onto that oxygen from that double bond. And because of that, because this compound shows resonance with this, where the oxygen has negative, right? That's another way to represent, or that's a different way that this compound is going to be represented in nature. It's going to be most of the time in this stable configuration, but some of the time it's going to exist as this, right? And because of that, this carbon wants to be attacked by a nucleophile, or a nucleophile wants to attack this carbon. And so what's going to happen is this nucleophile attacks this carbon, the electrons hop onto the oxygen picks up a negative charge from these two electrons in the double bond. this carbon now has a bond to this nucleophile. This Y is a good leaving group. It's going to leave, and basically what's happened is this nucleophile has replaced that leaving group, and that's all that this is talking about. Now we have acid halide synthesis. This is the exact same thing that I just told you, but it's with halides. So this Y over here is going to be one of the halides, so it's going to be like a chloride, right? So how do we form that acid halide? We're going to take that carboxylic acid. We're going to do I remember it as socyl. That's always how I remembered it in organic chemistry class, or like SOC. But basically you take SOCl2, and that's how you replace this with a chloride instead of the hydroxide. You can do the same thing with bromide with PBr3, and I kind of remember that as peanut butter, and that's how I remembered SOC and peanut butter, and that's how you take these carboxylic acids and you form them into a into like a carbonyl with a halide next to it. Okay, let's keep going. We're making good progress. Now we have reaction of carboxylic acid. So what's happening here is we have oxidation. This is nothing new. I told you about KMNO4. We went over all these oxidizing agents that take carboxylic acids, and they're producing carboxylic acids from oxidation of primary alcohols or aldehydes, or the oxidation of primary or secondary alkyl groups. So remember that we've already covered this. And actually most of this over here we've actually covered already, but let's go through that quickly. Nucleophilic acyl substitution, we just talked about that in detail. Nucleophiles we've kind of covered like really well, but here they're kind of introducing a few new terms for us. First is the ammonia amine. So ammonia and amines form amides. Amides are given the suffix amide. That's a pretty easy one to remember. And then cyclic amides, those are basically like the ones that are in cyclic compounds, right? Those are called lactams. Not that important that you know this right now. Actually, not at all important, but kind of like once you start med school, one of the things that you'll learn about is different types of antibiotics, and some of them are beta-lactamase inhibitors. Like lactams are in bacterial cell walls a lot, and so a lot of antibiotics that are targeting bacteria and infections, they'll try to target those like cell wall builders in bacteria cell walls that are using lactams. So that's kind of just an interesting tie-in. Then we have alcohols. Alcohols from esters. Remember, ester is that one where we have the C and then the double bond to the O and then another O, but then there's a continued ring on each side. So that those are esters. Esters are given the suffix -08. We've already talked about this. And then cyclic esters, so if it's in a ring, then we call that lactone. So lactams are when we have amides, and then lactones are when we have cyclic esters. Next we have carboxylic acids. Carboxylic acids form anhydrides. Both linear and cyclic anhydrides are given the suffix anhydride. Let me show you an example. Okay, this is basically what I was talking about by anhydrides, right? And how do we form this? We basically take two of those carboxylic acids, we put them next to each other, and what's happening is kind of like a dehydration reaction. You're taking out a water. And how do you take out the water? You're taking a hydroxide from one, and you're taking a hydrogen atom from another. You take them out, that forms a water, and then we have this as a result in an anhydride. So that's what I was talking about there. Now let's talk about reduction. Carboxylic acids can be reduced into a primary alcohol with strong reducing agents like LiAlH4. NaBH4 is not strong enough to reduce a carboxylic acid. So that's basically, you need to know that LiAlH4 is stronger than NaBH4, and we've talked about this on the previous page too. I will say that oxidizing agents and reducing agents are very high yield for the purposes of MCAT, and they'll probably have at least one question on this table. So I would try to know this table down cold, and if you just go back to the point in the video where I talked about this and gave you any frameworks to understand how do you think about PCC, how do you think about KMNO4, how do you think about this, how do you think about NaBH4, how do you think about LAH, those are all going to be really helpful, and I'm sure they came up in your organic chemistry class. So just do your best to review this table. It's going to be pretty helpful. All right. Okay, we talked about reduction. Let's talk about decarboxylation. Decarboxylation is when you're losing a carbon dioxide. So I talked about dehydration reactions when you're losing a water. Decarboxylation reactions are kind of similar, where you're losing a carbon as a carbon dioxide. Saponification is like when you think about soap, and I'll show you a Google image to help this get a little clearer in your head. But basically, you mix a lot of long-chain carboxylic acids with a strong base. And what's going to happen is the formation of a salt we call soap. Soaps are basically hydrophilic carboxylic heads and then hydrophobic alkyl chain tails. So how do you think about this? Well, basically there's going to be this, right? It's going to be with a negative charge because it's in the place of a base, right? The base takes out the hydrogen there. Remember, I told you that that hydrogen is happy to leave because this is a pretty acidic compound, right? And then we have this alkyl chain tail, right? Is this part going to be hydrophilic or hydrophobic? This part is going to be hydrophobic. This part, remember, it's carrying the negative charge because this hydrogen has been picked up. So this part is going to be hydrophilic, right? We have this long chain at the end, and we have this hydrophilic top. So basically what's going to happen is we have these oil droplets. So when you're like scrubbing your hands with soap, what's happening is that you have like all this dirt and oil and all these things, right? Those things are going to go in the middle, and all of these alkyl tails, which are hydrophobic, are going to surround that like oil droplet and all those things, right? Basically what's happening is that there's water on the outside. The water is hydrophilic. These carboxylic heads are hydrophilic, and these are hydrophobic. That's where the oil goes, and that's how soap helps you clean your hands, because you're basically taking out the oils and the dirt from and separating it from the water. Okay. Micelles are basically micelle, and I never know how to pronounce it, but basically those are just polar heads, nonpolar tails. We just talked about that, and that's how you dissolve nonpolar compounds like grease. Okay, now we talk about amide synthesis. So how do you form an amide? This is actually a really important compound, and you should be able to tell me why is this an important compound. I'll give you a second. And basically, why is this an important compound? The answer is right here. Basically, this is the process of protein synthesis. In proteins, as we'll talk about in biochemistry, there's amino acids. You line those amino acids together, and you have to do this reaction in order to form a polypeptide chain. And polypeptide chains are basically like hundreds of these amino acids that are all linked up. So what is that reaction happening? We have this NH2, the ammonia on this side, and then we have the carboxylic acid on this side, right? This reaction goes through, and then what's happening is that we have this that's lined up next to this. What's happening is that this OH leaves, and then one of the protons leaves from this. So we get water that's leaving, right? And there's a bond formed between this carbon over here and this nitrogen over here. And so that's what this is showing right here. That's that bond. That's a dipeptide. That's a dipeptide because it has two amino acids in that peptide chain. Okay. That's also a pretty high yield point for MCAT. Now we have anhydride synthesis. This is what I showed you on that Google image. So we're just taking two of these, and we're removing one OH and one water, and that's how we form this acetic anhydride over here. Now we have ester synthesis. Ester synthesis is this is basically the reaction. I'll show you a Google image to help it solidify better. So what's happening in this reaction is essentially, initially this was a carboxylic acid. Something probably like sodium hydroxide, a base, picked up that proton over here, and because of that, this oxygen now has a lone pair of electrons, and the hydrogen has gone away. Now what's happening is that we have this oxygen that's going to act like a nucleophile and attack this carbon over here. This CH3I, is there a leaving group? There is a good leaving group, which is this iodine, right? This iodine is going to attack this. It's going to form a bond here. The iodine is happy to leave, and so basically what's happened is that we've replaced the iodine over here with this molecule over here, the sodium butanate. And then the sodium and iodine, they form a bond, but in solution they're not going to exist together. They're just going to separate into sodium particles and iodine particles. So that's how you form methyl butanate. Okay. And then it's important to notice that what is this compound called? Is it a carboxylic acid? Is it ether? It's actually ester. So that's why we were showing ester synthesis, because we have that sort of configuration. Okay, amides is what we were talking about previously. Amides are also pretty important for your MCAT. Amides are when you have condensation products of carboxylic acids and ammonia or amines. amides are given the suffix amide, and the alkyl group on the substituted amide are written at the beginning of the name with a prefix of N. So cyclic amides are called lactams. That's what I was telling you with the beta-lactam antibiotics, and they're given with the Greek letter of the carbon forming the bond with the N. Not too important that you know the specific naming convention, but it is kind of helpful to walk through, like, why is this called this. So we have NN dimethyl propanamide. Let's walk through this. What does this compound look like? We have a amide at the end, so we know that there's an amide. That's what we see right here. That's an amide, right? We know that on that amide, on that nitrogen, there's a dimethyl. So we see that there's 2 methyl groups off that nitrogen. And then we have propane, which means we have 5 carbons on this chain. So we see 1 carbon, 2 carbon, 3 carbon, and then 4 carbon, 5 carbon. That's basically what they're saying by propanamide. Okay, next we have beta-lactam. Beta-lactam, remember I told you that lactams are cyclic amides. So cyclic amides, we still have that amide structure, but it's existing in a cyclic structure, and that's why we have beta-lactam. Okay, next we have esters. I've told you what esters are. Cyclic esters are called lactones, as we talked about before. And let's just review the structure. Isopropyl butanoate. Butanoate, we know that O8 suffix means that there's an ester right here. Isopropyl, remember in the beginning of this video I told you like those substituents that are important to remember. If you remember, isopropyl was one of those 4 substituents that I told you about. So we know that there's this isopropyl, and then there's a butanoate because there's a 4 carbon chain. Okay, now let's keep going. Anhydrides. I've showed you that Google image of the anhydride synthesis where you have the 2 carboxylic acids, and then you have that dehydration reaction, and that's how you form an anhydride. Okay, and then I guess kind of important mid-yield to know that 5 or 6 carbon membered rings are generally stable, so that's why you'll see these type of rings in compound. Okay, next I'm going to talk about Fischer esterification. I don't think that it's too high yield to know exactly all the steps in Fischer esterification. What I do think is a very important process that helped me a lot with organic chemistry for the MCAT a couple of years ago was going through all the steps of Fischer esterification and making sure that I could understand why is this occurring, and making sure that my foundation was solid enough so that I could understand like what are the steps. Basically what you need to know as a framework is that Fischer esterification is a process of taking a carboxylic acid like we see over here and forming a ester group, right? So we see an O, a carbon that's double bonded with an oxygen, right? That's an ester. So this is basically a process that we figured out, not we, but they figured out in organic chemistry, of how to take a carboxylic acid and form an ester. Now what's happening is that we take this compound, the carboxylic acid, and then we take this compound, right? This compound is kind of unstable because there's 2 hydrogens on that oxygen, and that oxygen doesn't really like it. It has that positive charge over here. What it wants is that it wants to get rid of one of these hydrogens, so this oxygen over here will pick it up. Because of that, now we'll have the positive charge on this oxygen over here. Again, not too stable, but it'll happen. And then this, now we see that this has picked up this hydrogen. Now this carbon has a double bond to this oxygen as well as single bonds to this carbon and this oxygen, right? So you can kind of see like we're getting to the process of forming an ester. Now we know that this carbon, remember that it's electrophilic, this oxygen over here is going to attack this carbon. What's happening now is that this oxygen now has a bond with this carbon. This carbon, the double bond, the electrons are going onto this oxygen. And so now we know that this oxygen has become, this OH is now going to become a hydroxyl group, so that's the same thing as this over here. This OH over here is the same thing as this OH over here. This carbon over here is the same thing as this carbon over here. And then this bond is represented by this bond over here. Okay, now that we formed this bond over here, you should notice that this oxygen now has 3 things that are attached to it, so it's going to have that positive charge. It's again going to want to get rid of this hydrogen, so it's going to get rid of one of these hydrogens, right? And this HOCH3 is going to pick it up again. All right, so now we have this compound right here. Based on all we've done is just gotten rid of this hydrogen over here. Now what's going to happen is that this OH hydroxyl is going to pick up one of these hydrogens from this thing over here. So this OH is going to pick up a hydrogen, and that's how we get to this spot over here. Now what's going to happen is that this is happy to leave. It's going to pick up the electrons from this bond, and then this, you should realize, is just water. So this leaves as water, right? We just get a water particle that's produced from this. Okay, so now I'll let it erase. This is gone by, and now we have this carbon that's attached to one hydroxyl group, one CH3, and then one OCH3. And you should see like, oh, we're getting closer and closer to that ester that we wanted. So now we have this guy, and it's relatively unstable. This carbon has a positive charge over here. And so what's going to happen is you should notice that this oxygen over here has one lone pair over there and then one lone pair over there. So one of these lone pairs is going to go and form a double bond. Now this oxygen is going to have a positive charge. Why? Because it has 1, 2, 3 bonds, right? And so now this hydrogen is again going to get picked up from this compound. So now that this hydrogen is getting picked up from this compound, now we have what we wanted all along, which is that ester. And so that's basically Fischer esterification. Not too important that you really understand or that you memorize all these steps, but it's important that you go through the process and understand what's going on in Fischer esterification. How do we take a carboxylic acid and form an ester at the end of it? All right, good job. Now let's go to synthesis of anhydrides via carboxylic acid condensation. Unfortunately, we've already talked about this on that Google image, so I'm just going to quickly walk through this again. This hydroxide group over here is going to attack this carbon. Remember that these two are the same compound. Essentially, they're just carboxylic acids. This one attacks this. They form a bond. You have this oxygen that has a negative charge, and then you have this oxygen that has a positive charge. This hydrogen atom falls apart. Now we have, I'll use my marker, this hydrogen goes away. That's what's represented over here. Now we have this negative charge on this oxygen, goes in, forms this double bond. This is happy to leave as water, and so basically what we're having is kind of this dehydration reaction. And so we have this dehydration reaction, this goes away, this negative charge becomes a double bond, and that's how you form this. I've already reviewed this in that Google image, which I think is a little bit more helpful than this this diagram over here. So just go back to that part of the video a few minutes ago where I was showing that Google image. All right, let's talk about reactivity principles. I think this is pretty high yield. All right, let's keep going. So reactivity principles, again, I'm saying that it's pretty high yield to know this part that I'm going through now, which is things that I've already been reviewing as I've been going on, such as induction, conjugation, steric hindrance. So you should understand most of these concepts already. In nucleophile substitution reactions, the reactivity is acid chlorides, number 1, then anhydrides, then esters, then amides, then carboxylates. I would say that it's really important to know this right here, just because reasoning through it yourself is kind of difficult, but just knowing the principle that, okay, acid chlorides are the most reactive in terms of nucleophilic substitution reactions, then it's anhydrides, then it's esters, then it's amides, then it's carboxylates. And what does this mean right here? Basically, when you have one of those, let me show you the reaction that we were talking about. When you have one of these reactions over here, and you want to figure out okay, there's a nucleophile that's substituting this Y leaving group, and let's say that this Y over here is a ester, or sorry, is a, let's say it's let's just say that this nucleophile is an acid chloride, right? When this nucleophile is attacking, it's going to be really a strong nucleophile because it's number 1 over here, versus amide is a little bit less reactive than an acid chloride. So that's basically reactivity principles. I would know this order right here really well. And I think once you do a few practice questions on the MCAT with this, you'll get a better sense of why is this helpful. Okay, next is steric hindrance. Steric hindrance describes when a reaction cannot proceed because substituents crowd the reactive site. Protecting groups like acetals, they can be used to increase steric hindrance, and you should understand that protecting groups basically in certain reactions, when we, let's say that we have this nucleophile, we have a nucleophile in our solution, and we have this compound over here, And we know that this nucleophile is going to want to attack and replace this Y, right? So what we might do, if we want to just keep this compound as is, we don't want that nucleophile to do that, is we replace this Y with a protecting group, and it's going to be something that's really, really bulky, right? So now this nucleophile, because this is such a bulky thing, it's not going to be as easy for this nucleophile to attack, right? So this reaction may or may not happen. It's probably less likely to happen when we're adding so much steric hindrance. And then at the end, when we get the final product, then we just replace that bulky thing with a Y. And that's basically what that is talking about over here. Okay, now we have induction. Induction refers to the uneven distribution of charge around across the sigma bond because of the differences in electronegativity. You should understand that the more electronegative groups in a carbonyl containing compound, the greater its reactivity. Why is that? Well, let's just think about like a CO and then something like chloride, right? This is going to be like pretty electronegative, and because of that, there's a carbonyl containing compound, and this carbon, it's going to be losing it's like in this bond, the oxygen is going to be having more of a negative charge over here, and then this chloride is also going to be electron withdrawing. So this carbonyl is going to be more positive, right? The electrons are going to be distributed this way and this way. So that's basically what that's talking about. Conjugation is like what I've been talking about this whole time. It refers to the presence of alternating single and multiple bonds, which creates delocalized pi electrons. Pi electrons exist in those clouds that are above or below the plane of molecule. So if this is the bond, right, then there's going to be a pi orbital that's existing above and below. Whereas we represent sigma bonds, those electrons are existing in between these two atoms. Okay, electrons experience resonance through the unhybridized p orbitals, increasing stability. Conjugated carbonyl compounds are more reactive because they can stabilize their transition states. So the most important thing I would notice here is that conjugated carbonyl compounds are more reactive because they can stabilize their transition states. That's pretty important to know, and that's basically what we've been talking about this whole time. Now, ring states, okay, I guess I should explain this a little more. So basically what's happening is that when we're in a transition states generally are unstable. Like, let's say that I have this thing, right, and in order to do something, I have to attack this carbon, and during that time, this is going to have a negative charge, right? And because these electrons have gone to that oxygen. That's a transition state. Most of the time, transition states are unstable because it's process of going from one compound to another compound, and the other compound is going to be stable. But on the process, there's going to be an unstable intermediate. When you can make this intermediate more stable, this reaction is more favorable, and so this thing is more reactive in the beginning because it's more willing to undergo that transition. That's what this thing is saying here, is that when you have conjugated carbonyl compounds, it's more reactive because this transition state is going to be more stable. That's basically what that's saying. Now we have ring strain. Ring strain is due to torsional strain from eclipsing interactions at angle strain. And you can imagine that if I have like a compound like this, right, there's a lot of strain on these bonds because these carbons are just there's just like not a lot of like leeway in those angles versus like if I have this compound, there's a little bit more flexibility in those compounds versus like this or this. There's a lot of torsional strain in that. All right. Now we have nucleophilic acyl substitutions. I've already talked about this a lot on the previous page. And we just need to know what is the rate at which those reactions happen. They're based on their relative reactivities. So cleavage basically talks about anhydrides. Anhydrides, remember, are those things with when the two carboxylic acids form together. And cleavage basically refers to the fact that we can cleave those anhydrides by the addition of a nucleophile. Addition of ammonia or amine results in an amide. Amide, remember, is when you have that nitrogen next to a carbonyl. Amide and a carboxylic acid, and addition of an alcohol results in an ester and a carboxylic acid. Addition of water results in 2 carboxylic acids. I think this is kind of important, so I'm going to show you a few examples because that'll be more helpful. So I think this is a pretty good diagram showing anhydride cleavage. This is an anhydride right here, and you can see that we can form esters, we can form amides, we can form carboxylic acids, and we can form carboxylates. Here, if we add a hydroxide, then we get a carboxylate. If we add a water, then we get carboxylic acid. If we add ammonia, then we get an amide, and if we add this alcohol, then we get an ester. So that's kind of what this is referring to. There's multiple different ways that we can cleave a anhydride. Now we have transesterases, and transesterases are when you exchange one esterifying group for another on an ester, and the attacking nucleophile is an alcohol. So what does this mean? Basically, you have this. I'll show you an example that'll be more helpful. So this is basically transesterification reaction. You have this right here, which is an ester, and then you have this thing right here, which is an alcohol. You add these two together, and what's happening is that now we're going to get this right here, this one carbon chain, to be replaced by this two carbon chain, one carbon right here, one carbon right here. So that's what's happening over here. This guy leaves as a like this one carbon plus the oxygen leaves as a methanol, right? So this over here is getting replaced by this over here. That's what transesterification is referring to, and it happens when you combine an an ester with an alcohol, and you just replace one ester with another ester. Okay. Now we have amides. Amides can be hydrolyzed to carboxylic acids under strongly acidic or basic conditions. The attacking nucleophile is water or the hydroxide ion. That should make sense to you. Basically what's happening is that the amide is going to be hydrolyzed, and the amide is basically converting to a carboxylic acid. That happens when you have acidic or basic conditions. Okay, let's keep going. All right, more review things that I've referred to already. I told you about amino acids. Amino acids has an amino group. It has this variable side chain that defines the amino acid. Which one are we talking about? Are we talking about glutamate, or are we talking about lysine, or are we talking about glargine? And then we have this carboxylic acid group. This carbon over here, that's the middle carbon, is the alpha carbon. And then all amino acids are chiral except for glycine. You should be able to tell me if you watch, or if you understand biochemistry, you should be able to tell me why is glycine not chiral. And the reason why glycine is not chiral is because there's this side chain is a hydrogen, and so there's two hydrogens off this carbon, and so this carbon is not actually a chiral center, and so because that is not a chiral center, this compound is not chiral. Okay, all amino acids in eukaryotes are L-amino acids, and then they all have S stereochemistry except for cysteine, which is R. Not too important until you get to med school that you know this. Amphoteric is basically referring to the fact that amino acids themselves are amphoteric. They can act as both acids and bases. Where do you think that happens? Before you read this, you should be able to tell me, like, why is that true? And the reason is kind of in the name. Carboxylic acids are acidic, and then the amino groups, those are basic. And so that's why these are always really interesting for biochemistry questions, because this is an amphoteric molecule, right? This has acidic properties and basic properties. And then in neutral solutions, amino acids exist as Zwitter ions. Basically what's happening is if we have a pH of 7, like in your body, which is close to 7, what's happening, or your blood pH, what's happening is that this exists as a negative charge over here, and this exists as a positive charge over here. And so that's what's a Zwitter ion, but the ultimate full charge is going to be 0, unless it's one of those compounds where this side chain is going to be positively or negatively charged. But most of the amino acids exist as Zwitter ions. Okay, now aliphatic, those are non-aromatic. The side chains only include carbon and hydrogen. And I wish I could tell you that you don't need to memorize all this, but for the MCAT, it is really important that you memorize all the amino acids and how they're represented. And I'll try to go through helpful ways to memorize all of them in the biochemistry video. Now, peptide bonds are formed by condensation reactions that are cleaved hydrolytically. Resonance of peptide bonds restricts motion around the carbon-nitrogen bond, which takes on a partial double bond nature. You should understand why that's true. So let's look at this. So we know that in a peptide bond, this carbon over here is bonded to this nitrogen over here on a different molecule. So if I had a different amino acid right here, and the nitrogen was right here, this carbon over here would be bonded to this nitrogen over here. Why does that bond, even though we know it's a single bond, why does it have double bonded nature? Why does it have nature of a double bond? The reason for that is because there is resonance. These electrons over here can go onto this oxygen. This forms a negative charge. This nitrogen is actually, we can have resonance here where it takes a partial double bond nature. I can show you an image if that'll be helpful. But basically know that a strong acid or base is needed to cleave a peptide bond. It's not going to exist in just a hydrophobic solution, but if you have a strong acid or base, you can cleave that peptide bond, and that's formed when N-terminus of the amino acid nucleophilically attacks the C-terminus of another amino acid. Okay. Now, polypeptides are made up of multiple amino acids that are linked by peptide bonds, and then proteins are fully functional, large folded polypeptides. So what's the difference between a polypeptide and protein? That's getting into biochemistry, but basically we have these like alpha chains and beta plated sheets, and all of these amino acids have these R side chains, and they're all going to like fold based on their interactions with each other, and then we're going to have like the sulfur molecules form these covalent bonds, and finally we'll get this fully functional protein, and that's basically how we form proteins. Synthesis of alpha amino acids, they're basically formed in many ways. It's not too important that you understand all of these, like Strecker or Gabriel synthesis, but I'm going to do my best to just kind of walk you through what these are talking about and what's going on with Strecker and Gabriel synthesis. Okay, so Strecker synthesis, I think for both of these, it's more helpful to look at examples. And because these are relatively low yield, I think what's more important is you just understand what these are used for. And so ultimately what these are used for is synthesizing amino acids. How do you make an amino acid? How do you make one of those things where you have a carbon attached to an R group, where you're attached to, on one side, an amino group, and another side you're attached to a carboxylic acid? The first way is Strecker synthesis, and what you're doing is you're using this NH4CN compound, and you're doing it in water, and what's happening is you take this aldehyde, you use this NH4CN, you convert it into this compound right here, where this double bond to oxygen is getting replaced with single bonds to cyanide, and then ammonia, and then you add heat, and you add basically H3O plus, and what happens is that this guy picks up a proton, and then this CN gets converted to carbon dioxide, or not carbon dioxide, but CO2 minus. And what this is a carboxylic acid. I misspoke, not a carbon dioxide, carboxylic acid. And you can see here, this is what an amino acid is. This is a carbon attached to an R group, and this is that center carbon, the chiral carbon, and it's attached to one amino group and one carboxylic acid group. Now, you might be thinking, like, how does this actually happen? How does this cyanide get converted to carboxylic acid? How does this all happen? And truth be told, I don't know, and I don't think you need to know for the MCAT. How this process occurs is beyond what you need to know. What's more important is that you kind of understand, okay, we're using NH4CN, we're using protons, and basically we're converting this aldehyde into an alpha amino acid. Gabriel synthesis is basically even more complicated than that, and basically what you're doing, I'm going to show you some examples because it'll make more sense, and these are some of the best examples that I could find. But basically what you're doing is you're doing a series of these 3 steps, and when I was learning in my organic chemistry class, we always just kind of talked about, okay, we'll do Gabriel synthesis on this, or we'll do Gabriel synthesis on this, and that's kind of what we had to know. We didn't really need to know like all the different steps and all those things. And so if that's kind of what you needed to know for your organic chemistry class, then for sure you're going to need to know less for the MCAT. So this is again Gabriel synthesis, and I would just recommend taking a few look at some examples, but the main thing is I would try to understand that these are kind of, this is what's going on, that you're doing this or you're doing this, and you're using these specific compounds, but basically you should be able to understand like what's going on. I think what's more important for the purposes of Strecker synthesis versus Gabriel synthesis is you should be able to understand when you choose to do which one. Like, when do you choose to do Strecker versus when do you choose to do Gabriel, and you should kind of just understand the general idea behind it, but you don't need to understand how they work. All right, so now we have phosphorus containing compounds. Phosphoric acid, sometimes referred to as a phosphate group, or inorganic phosphate, is denoted by Pi. Very important in biochemistry in our body. You have dihydrogen phosphate, you have hydrogen phosphate, you have inorganic phosphate, you have phosphoric acid structure, which contains 3 hydrogens, and each of those hydrogens has a unique pKa, right? Different acidities for each of those hydrogens on that phosphoric acid, and that's why when you do that titration curve, you're going to see multiple drops, because each drop is representing a different pKa. I guess I should say multiple rises for phosphoric acid. Now we have phosphodiester bonds. Phosphodiester bonds is basically what forms the backbone of the DNA. If you remember in biochemistry, there's these phosphate groups, right? And then you have the rest of the DNA particles, and basically the backbone is formed by these phosphodiester bonds. And in forming these bonds, you have pyrophosphate is released. And so how you think about this is usually there's those 3 phosphate groups, right? 1, 2, 3 on that nucleotide base. So you have 1, 2, 3 on a nucleotide base, right? And what's happening is that when you have to get rid of 2 of those phosphates in order for this phosphodiester bond to form. And so when you do that, you're getting rid of a pyrophosphate, or 2 inorganic phosphates. Pyrophosphates can then be hydrolyzed into 2 inorganic phosphates. So that's basically when you take this 2 phosphates and you split them up into individual inorganic phosphates. Phosphate bonds are high energy because of large negative charges in adjacent phosphate groups and resonance stabilization of those phosphates. Okay. Organic phosphates is when you have carbon-containing compounds that have phosphate groups. The most important ones that you should know is ATP, GTP, and DNA. So those are organic phosphates. All right, almost done. So we have infrared spectroscopy. I would highly recommend that you look at a lot of examples to get a better idea of this, because if you don't remember this from your organic chemistry class, it's probably going to show up one way or the other. It's more important that you understand this table than anything else. So you should know that NH is 3300 and it's a sharp peak. You should know OH is 3000 to 3300 and it's broad. This is probably the most important one, that it's probably going to show up if any of these show up. This is also kind of important, the 1750 sharp, and then this is also sort of important, the CC, the 1600 to 1680 weak one. And so if they give you an IR spectrum, probably not going to show you an IR spectrum, but they might show you, I think they did show me on my MCAT, then you should be able to say like, okay, I see this broad stretch around 3300, that has to be OH. And then I see like around, I don't know what this is, like 11 or 1200, I see this, this strong stretch, so it's probably a CO. And you should kind of understand like, okay, in some of these, this will be like moved one way or the other. So like in a cyclohexanol perhaps, or in the OH, in the presence of OH, the CO might be shifted left or right. But in general, you should just kind of be able to look at some of these spectrums on Google Image and try to figure out like, okay, what compound is this? And if you can do that, then you'll be solid. This is another example, benzaldehyde, and you can see that based on where these peaks, so this is kind of the classic, 1750 narrow sharp peak, right? It's over here, the sharp 1750, and that should tell you, okay, there's a C double bonded to O. So that's like a really good hint. Another one is this aldehyde over here, right? And it's not in this table, but basically the aldehyde is going to look kind of like this, around like 2800 or so, and that should tell you like, okay, there's probably an aldehyde based on this carbonyl, this C double bonded to O, and then this CH with the aldehyde. So we're probably looking at something like benzaldehyde. So just kind of get comfortable with IR spectrums, look at them on Google Images or look at a website, and that'll help you. Now we have UV spectroscopy. UV spectroscopy are more important for understanding double bonds or heteroatoms with lone pairs that create conjugated systems. And they measure the absorption of UV light And UV light is basically causing the movement of electrons between molecular orbitals, like we talked about in general chemistry. UV spectra are generally plotted as percentage transmittance or absorbance versus wavelength. You should know that there's HOMO and LUMO. In order to appear on a UV spectrum, a molecule has to have a small enough energy difference between its HOMO and LUMO. HOMO is high energy, LUMO is low energy, and they're basically talking about different molecular orbitals. So it has to have a minimum enough energy to allow an electron to move from one orbital to the other. And the smaller the difference, the longer the wavelengths are going to be able to absorb. Why does that make sense? Because the longer the wavelength, the smaller the energy. So that should make sense based on our discussion in general chemistry. And so that's why that's true. Now we have nuclear magnetic resonance spectroscopy. So important to know here that NMR spectroscopy measures the alignment of nuclear spin with an applied magnetic field, which depends on the magnetic environment of the nucleus itself. It's useful for determining the structure and connectivity of a compound, including functional groups. And it's generally plotted as frequency versus absorption, and they are standardized by chemical shift in parts per million of spectrophotometer frequency. So I guess probably the most helpful will be to show you some examples. So again, you're not going to be asked too many questions on NMR spectroscopy, but I'm just going to go over the high yield points in this example. So the first thing to know is there's shifting, and we'll talk about upshift versus downshift. And then there's the idea, this is a hydrogen, by the way, but there's the idea of splitting. And so this is a singlet over here. And the reason why it's a singlet is because there's no hydrogens on the adjacent carbon. And so if we look at this compound over here, this is the carbon it's talking about. These are the hydrogens it's talking about. And the reason why this is a single peak over here is because there's no hydrogens on this adjacent carbon, right? Now let's talk about this one over here. So this is talking about this guy. And remember, you can figure it out based on like where it's aligned. So is it shifted this way or this way? We know that this 4 is giving us some details about what this is, what like structures is around this. But basically, why is this having this many splitting? And the reason why 1, 2, 3, 4 is because it's next to the adjacent carbon has 3 hydrogens next to it. And so 1, 2, 3 plus 1 gives us 4. That's basically how we do splitting. Now let's talk about this guy. Why is it a triplet? The triplet is because on the adjacent carbon, so this is the carbon we're talking about, on the adjacent carbon there's 1, 2. So 2 plus 1, that's why we get a triplet. So that's why we see 3 peaks. Those are kind of the high yield points. The final high yield point is that you should probably remember like some of the principles behind which way shifts this way and which way shifts this way, and you'll be good on NMR spectroscopy. Some high yield, very quick points. TMS is kind of tetramethylsilane, and that's just the chemical shift of 0. That's how we calibrate it. Integration is the area under the curve, and it's proportional to the number of protons contained under the peak. So if you look back here, this one, the area under the curve gives us more information about the number of protons under that peak. And so that's why we see like different areas under the curve. Okay, now we have deshielding. Deshielding occurs when electron withdrawing groups pull electron density away from the proton nucleus and allowing it to be more easily affected by the magnetic field. Now it's very important that you understand that electron withdrawing groups are going to make the peak further downfield. Downfield means left, and deshielded by electron withdrawing groups are electronegative atoms nearby. That shifts this left. So let's go back to our diagram. In our example, if we see electronegative or electron withdrawing groups, then it's going to shift it to the left. And so that should kind of make sense. Let's look at our example. So we have this carbon with this ester over here. And so we can see that the one that's closest, the one that's on the right the most, is the one that's furthest away from this ester group right here, right? The one that's shifted the most to the left is this one right next to that oxygen over here. So that should make sense to you. All right. Now, obviously, the other way around, upfield is going to be right, and it's more shielded by electron donating groups or less electronegative atoms nearby. Then we finally have spin-spin coupling, which is what I was telling you about. A proton's peaks is split into n plus 1 subpeaks, where n is the number of protons that are 3 bonds away from the proton of interest, so it's on the adjacent carbon. And then I would try to look at a couple of NMR spectroscopies and try to understand what we're looking at. Same thing with, again, look at infrared spectrums and then look at ultraviolet spectroscopy. Now, you might not get too many questions on this, but it'll be really helpful for the purposes of your Orgo class, as well as maybe getting 1 or 2 more questions right on your Orgo section. All right, mass spec is just another way where we can figure out what is the molecular weight and then aid in determining molecular structure. So we can kind of get like a better idea of like, oh, is there a bromine on this or is there a chloride on this? Those types of things. The base peak is the tallest peak. It's not always like the most intact molecule, but it's just the tallest one. Molecular ion peak is the one that represents the molecule itself. And then the M+1 peak is the relative abundance of carbon-13. It's found in the abundance of 1.1%. So if the M+1 has a M/Z value of 4.4, that means that there are 4 carbons. So that should kind of make sense to you. But just in general, if that doesn't make sense, just remember that like if it's 4.4, that means that it's 4 carbons. If it's 8.8, then it means 8 carbons. M+2 peak tells you the relative abundance of either 81 bromide or 37 chloride. Bromide has a 1-to-1 ratio relative to the M peak, and chloride has a 3-to-1 ratio relative to the M peak. So let's look at 1 or 2 examples. Okay, so I'm going to go very briefly into this example. It's not super high yield, all these imaging for the MCAT, so that's why I'm going a little bit faster through it. But very briefly, you can see that basically this is representing when we put this through the machine and it breaks up into all these fragments. We're trying to piece together more of a framework of how we can figure out what molecule we're looking at. So we already know the answer. This is the molecule we're looking at, but how would we try to figure that out? Well, first of all, I see like a peak around 81. And remember, there's the 1-to-1 ratio. And so I'm pretty sure that there's a bromine in this particle just because there's going to be this bromine fragment. So that's number 1. Number 2 is I see like a lot around 28, 29. And so there's this fragment over here. I also see like a lot, some around like 14, 15. And so CH3CH2. If we figure out what's the mass of that, that's going to be around 29. And so that's why I'm going to be having a strong suspicion that one of the fragments is going to be that CH3CH2, just this, right? So kind of based on those pieces of information, you can kind of piece together that this is going to be the molecule of interest. And that's kind of all I'm going to cover around mass spectrometry. I think that if you want to learn more about all of these types of imaging, like infrared, NMR, and then mass spectrometry, it's going to be more helpful to go through like the Orgo videos on YouTube, like the Orgo tutor, and watch some of his videos because those are really good and really detailed into all these different types of imaging. But for the purpose of MCAT, again, it's not super important that you know like how to figure out what molecule you're looking at. But generally, if you know these basic principles, like the fact that downfield is left, upfield is right, and then you know that deshielding by electro withdrawing groups, and then more shielded by less electron negative groups, and then you know like this table over here, that's going to be sufficient for the MCAT. Okay, almost done. We know solubility-based methods, and if you remember what I was talking about soap, that's going to help you a lot here. Extraction is when we combine 2 immiscible liquids, one of which easily dissolves in the compound of interest. So we have a non-polar layer and a polar layer. The polar layer is usually water or some other aqueous layer. The non-polar layer is organic layer. It dissolves non-polar compounds, simple enough. Aqueous layers like water dissolves things with hydrogen bonding or polarity. Wash is the reverse of extraction. It's basically when you take a small amount of solvent and you dissolve any impurities that run over the compound of interest. So if I have a compound of interest that's non-polar and I want to get rid of like any of the polar impurities in there, I would just run some water through it, and hopefully that would get rid of those polar impurities. Then there's filtration. Filtration isolates a solid from a liquid. There's 2 types, gravity and vacuum, and hopefully in your organic chemistry laboratory classes you did a vacuum filtration, and so you should be able to like remember what those are. Gravity filtration is when you use the product of interest in the filtrate. Use when the product of interest is in the filtrate, and there's hot solvent that's used to maintain solubility. You should remember that from your organic chemistry class. And then there's vacuum filtration. Vacuum filtration is used when the product of interest is the solid. So in this case, use when the product of interest is in the filtrate versus when it's the solid. A vacuum is connected to the flask and it pulls out the solvent through more quickly. And so I'll show you an example of both. So this is a good example of gravity filtration right here. It's very simple. You just have filter paper, you have that stem funnel, you have solid particles inside, and then you just dump liquid, and then you just use gravity, and the liquid falls down. At the bottom, you'll have the liquid molecules as well as dissolved ions. And then you have vacuum filtration. Vacuum filtration, this is kind of a more complicated example, but this will work also. This is on the right here is vacuum filtration, and you'll just notice that there's a vacuum that's plugged into it, and you should remember what it does. Vacuum filtration is used when the product of interest is the solid, and the vacuum is basically used to pull the solvent through more quickly. All right, now we know recrystallization. Recrystallization is when the product is dissolved in a minimum amount of hot solvent, and then if there's impurities, if the impurities are more soluble, then the crystal will reform while the flask cools, excluding the impurities. Basically, what you're hoping for is that the impurities are just staying soluble in the liquid, and then the crystals are reforming, and so now these crystals are going to be pure, and all the impurities are going to remain in that liquid. Now we have chromatography. Chromatography is when you separate two or more molecules from a mixture. There's liquid, gas, size exclusion, ion exclusion, affinity, and thin layer chromatography. And when I go through the appendix, you'll get more information on that. But basically, you should just know that chromatography is how you take two different types of molecules and you separate them. And there's different machines for each one of these. Finally, there's distillation. Distillation is when you separate liquids according to their differences in boiling point. And the liquid that vaporizes first is the one that has the lower boiling point, and it's collected is called the distillate. So when it's you'll basically heat up this liquid. Some of it will go on to this other side. That's going to be called the distillate. What's left over is going to be that different liquid. So because these two liquids in the mixture have different boiling points, you're able to separate them. Simple distillation can be used if the boiling points are under 150 and they're at least 25 degrees apart. Then there's vacuum distillation. This is when the boiling points are over 150, and this helps to prevent the degradation of the product. The vacuum is basically, you should remember, like PV-nRT, based on that, the vacuum is lowering the air pressure and it decreases the temperature at which the liquid starts to boil. And then there's fractional distillation. This is used when the boiling points are less than 25 degrees apart, because it's basically a way to allow more refined separation of liquids by the boiling point. Because if they're only like 10 degrees apart or so, you need to use something more refined, like fractional distillation. In most experiments, you have organic at top and aqueous at the bottom. The aqueous is going to have the higher density. Organic is going to have the lower density. Not always true. And then you have the Erlenmeyer flask, and that higher density liquid is falling through first. Extraction is when you have polar solutes dissolved in aqueous layer, and then non-polar solutes dissolved in the organic layer. All right, I hope that was really helpful for you. Again, there's a YouTube channel called the Organic Chemistry Tutor. It's really good for understanding anything that you feel like wasn't fully covered and you want some examples. I would recommend going through this yourself and then trying to use like that Google image method and YouTube method, where you look at specific topics that you don't fully understand and just trying to like find Google images that'll solidify that connection in your brain. And then again, just do questions for organic chemistry. It's going to help you a lot more than reviewing this, because when you do questions, you're actually trying to figure out how do you synthesize one compound into the other, and it's going to help you out a lot. All right, I hope that was really helpful for organic chemistry. If you don't mind, hit the subscribe button. I'd really appreciate it, and I'll see you in the next video. Bye, everybody.